this final conference today. I'm happy you are all with us. And I would like to welcome everyone to the final event of the BioS project, which, as many of you know, is a project co-funded by the European Commission and stands for Digital Skills on Computational Biology for Healthcare Professionals. My name is Laura Dawn. I am the project coordinator of the BioS project, and today I will guide you through this event. I'm very happy you joined us today, and I hope you find the input interesting and relevant. Let me start by briefly outlining our event agenda in order to give you an idea of what is expecting you today. We will start with 3 expert talks on highly topical issues, starting with Dr. Ferran Casals from Bioinformatics Barcelona Association on opportunities for bioinformatics-based approaches in the diagnostics, followed by another interesting speech on bioinformatics and combating COVID-19, presented by Dr. Csaba Ortatai from Hereditary. Our third expert is Dr. Dimitrios Doltsinos from John Radcliffe Hospital of the University of Oxford, speaking about the application of bioinformatics in cancer patient treatment. After this, we will have a 20-minute Q&A session with the 3 experts. You can post your questions to them at any time in the chat below. For this, please open the chat window in below right corner and type in your questions. We have a team collecting your questions. And if time does not allow to reply to all your questions, you will receive a Q&A document with all the replies from the experts after the event by email. The second part of our event is the presentation of the BioS project and its result. This will be presented by me and other project partners who I will proudly introduce during this session. And then the third part of the event is a workshop on understanding the genetic basis of diseases for precise therapeutic recommendations. The workshop will be held by our project partner INS Application and the German Oncology Center. Next slide, please. Just to give you a few words on technical issues, the event will be recorded and the recordings will be published on our website and the BioS social media channels. Also, the PowerPoint presentations you are seeing today will be uploaded after the event. For all questions you might have during the event, you can either use the chat function, as I just described before, or if you prefer, you can use Twitter and post your questions under the hashtag BioSFinalEvent. And of course, we're always looking forward to receive your feedback, so please make sure you respond to our questions after the event. If you want more information about the BioS project or the course, or if you have any other additional questions, please visit www.bios-project.eu or contact me personally under my email address, laura.dorn@stw.de. And now, before we start with our expert talk, I would appreciate if you try out our question-answer function. This way we get to know you a little bit, and I try out this function as well. Give me 1 second. The question should pop up. Right here. And you can respond directly. Okay, we have quite a few. Yeah. Okay, so we have 14 who already participated in the BioS course. So you know a little bit about BioS project and obviously about the BioS course and the content. And there are 9 who responded who have not yet participated in the BioS course. But this can obviously change. So, and then I have one more question for you, which appears now. Do you apply bioinformatics at your work? Okay, and here we have almost even, yeah. So we have 13 already applying bioinformatics and 11 who do not. Okay, very interesting. Thanks for having taken part in this short questionnaire. And now I'm pleased to introduce to you Dr. Ferran Casals from Bioinformatics Barcelona Association, who is one of our experts in bioinformatics and supported the creation of the BioS course. Dear Ferran, the floor is yours. And you are
Hi,
muted.
everyone. Thanks for this introduction. Well, and thanks also to all these project members for this collaboration in such an interesting project. Well, as someone working in genomics, I would like to discuss in the next few minutes on how relevant is bioinformatics for the genomics field. So if we can show the slides, please. Okay, thank you very much. There we go. Okay, well, in fact, bioinformatics has become essential in many research fields related to biomedicine, to the point that not being just a tool, but a whole discipline by itself of research. The example of genomics, I would say, is paradigmatic. You might be aware of these sequencing technologies that were called next generation sequencing technologies that have changed completely the way of thinking that we have in genomics and medical genetics. This is just the title of one manuscript in 2008, when with the arrival of these technologies. What happened is that suddenly we moved to a new scenario where we could sequence almost everything. Okay, so the increase of the capacity of sequencing was in orders of magnitude. Okay, to do a comparison, the first release of the human genome was in 2001. It took 15 years of work. It took $1 million and hundreds of laboratories. Today, you can have your genome in 2 days in one lab with one technician working on this, one bioinformatician also, and just by 1,000 euros. Okay, so while sequencing, I would say it's trivial, or at least is relatively cheap and fast. The bottleneck now, the challenge is in bioinformatics. It's how we store, how we analyze, how we process all this data that we are producing. At the end, what we want to do is transform the quantity of data, terabytes and petabytes of data, in a list of genomic variants. So positions where a given individual is different to another individual in the population. Okay. I don't know if you know how many variants do you have on your genome, but each one of us in this room, we have about 3 million of genomic variants in our genome, okay? Of different types, and by far, the most common type of genetic variants are the single nucleotide polymorphisms. Okay. Thanks to this big capacity of sequencing, some big efforts, like the 1,000 genome projects, change also our vision of the human genetic variation. I would say in 2000, we were in this paradigm that human populations are similar genetically, and they are also. So the message is that we are still consider we are very similar, but thanks to this big capacity of sequencing and them, thanks to bioinformatics, we have discovered that a very important part of the genomic variation is rare. That is, it's not shared across population. This is important because, as you will see in the next slides, rare variation is usually linked to genetic disease, and it's important to understand the fact that this genetic variation producing disease often is not shared across human populations. Okay. So before I start talking about genetic disorders, let's see this very simple slide about the different models of genetic disease. What we first do in genetics is to differentiate the diseases according to the prevalence, to the frequency in the population. And we do a very strong differentiation between common disorders, those above a certain threshold of frequency in the population, and the rare disorders. And we do this differentiation because the genetic model, okay, explaining these diseases is very different. While in common disorder, we have the small contribution of many genetic factors, in rare disorders, what we have often is the contribution of a single gene to this disease. So the way of designing or of making a diagnosis is completely different in common and in rare disorders. The same at the level of the genetic variants. The genetic variants generating monogenic disorders are usually very infrequent in the population. They have a high penetrance, and at the other side, we have more common genetic variants generating common disorders. But the key point here is how we move from these 3 million genetic variants that any of us has in the genome to this, the one causal genome variant that it's originating the disease. And this is where we need, again, bioinformatics. We have needed bioinformatics to process all this quantity of data we are generating with the next generation sequencing technology. And now we need bioinformatics to make sense of all this data. So for many years, we have been doing these comparisons of that finding a gene related to a disease is like finding the needle in the stack. So it's finding the one variant among these 3 million variants. So this is what is called functional annotation. So we need bioinformatics to predict the impact of genetic variants in our genome and in our proteins and in our phenotype or in our features, if this is the case. There is a huge variety of bioinformatic methods, tens of them using different properties of the genetic variants. Well, here you have a list, but it's more extended than this, but there are tens of methods doing this. And as you can see, what these methods do is integrating, and this is a key word in medical genomics. We have to integrate many different sources of information. Okay, and you see any one of these methods, which kind of information is integrating, from physicochemical, structural, evolutionary information. This is very important, or the simple we can do by predicting the effect of a missense genetic variant. Okay, so as I have said a few slides ago, we do a very important differentiation between common genetic variant, common disease, and rare disease, where genomics and bioinformatics have had a most important impact in the last year has been in rare disorders. Okay, in common disorders, we are still discovering many genetic variants that are associated to disease, but as I said before, the individual contribution of each one of these variants is very small. All of us will have these genetic factors. At the end, what we do is integrating this contribution of hundreds or even thousands of particular genetic variants into what is called polygenic risk scores. But still, the clinical significance of them is not very important. Okay, as I have said, where genomics had a very important impact has been in rare disorders. Okay, yes, and thanks to these technologies from 2000, we have discovered the origin of many rare disorders. The success rate on the discovery of the genetic origin of rare disorders is very unequal, and it changes depending on the type of disorder. But I would say we have discovered the origin between 20 and 50% of the diseases. But still, we need to explain the remaining. No, we need to explain this 50%, more or less, that we have not been able to explain, even if we have sequenced the whole exome or the whole genome. So, in the last slides I will just give you two new ideas. So what we do with patients, we need to imagine a new scenario for the disease, okay? And two of them are the contribution of somatic genetic variation and the contribution of more than one gene to genetic disorders. as you can imagine, each one of these new theories or each one of these new hypotheses comes with new experimental, analytical, and bioinformatic approaches to unravel the origin of the genetic disorders. As I have said, one of them is the contribution of somatic variation. Whenever we heard somatic variation, we link this to cancer, okay? So the disease by excellence where somatic variation is involved. In cancer, most of the bioinformatic tools that we have for the analysis of disease, they need to be adapted to the particular situation of cancer, and we need new annotation tools to predict the effect of these genetic variants. What I want to say is that we have seen, again, thanks to this sequencing capacity, that the model of somatic variation, that is, genetic variation that we have but has not been inherited from our father or our mother, can be extended also to other diseases. So from the moment we're a zygote, we start to replicate. You can see this in one of the videos of the BioS project. From this moment, we start to accumulate new mutations. So it has changed the vision of our genome, not as a static entity, but as a dynamic entity, because we keep losing and gaining new genetic variants that can be related to disease. For this, the big challenge here is that these variants are in our cells, but they are found in smaller frequencies than the germinal variants. In other words, if you have a mutation or a genetic variant from your father, it will be in 50% of your cells. If you have a new genetic variant that appeared when you were 40, for example, it will be present in a small proportion of cells. So if you don't sequence the target, the tissue of interest, or you don't sequence with enough sequencing coverage, you will not detect them. Okay, so we need to sequence with very strong coverage the genomes to discover the somatic variation. As I have said, this model again is not restricted to cancer. And for example, in my field, in primary immunodeficiencies, we have reported recently that it's more extended than it was thought previously. And the other model that is becoming popular in I would say in the last 2 or 3 years is the Genic Contribution. Often when we think in rare disease, the genetic model is quite simple. It's a Mendelian recessive where the parents are healthy carriers and the son or the daughter receive the 2 copies that produce an abnormal protein. But why not having this protein here to the left where, yes, child has 2 copies, 2 mutations, 1 from each parent, but not in the same gene, in different genes. So genes that, for example, the protein interacts in a complex, and in 2 of the genes, this complex is not functional. Here, again, we need bioinformatics because we have a new field where we have to work a lot that is in the field of the connectome or the interactome. I need to know this gene that I'm looking at. I need to know which proteins is interacting or sharing some functional capacity or sharing some metabolic pathway, for example. Okay, so here we need again the field of bioinformatics. Well, I hope with this I have given you a general idea of what we do thanks to bioinformatics in the field of medical genomics. Let me finish with some key ideas. Referring mostly to bioinformatics that is essential for the analysis of genomic data. At the beginning, from primary analysis of the amounts of data to genetic variant calling. Once we have genetic variants, we need, again, bioinformatics for functional annotation. Most of these 3 million variants that we have are neutral. They don't have any effect. But we need bioinformatics to predict which variants have an effect. We need to explore new genetic models of monogenic inheritance and explore the interactome and the human connectome. And again, this keyword, we need to integrate information from many, many different fields, and this is only possible with bioinformatics. Let me finish with the best conclusion, is that, well, with the arrival of new technology in bioinformatics, we have a need in the field that it's training. And we need training, I would say, and maybe I could open this question for debate. in two senses. We need training young people to be efficient bioinformatics, for example, in a hospital environment, but we need also training health professional at least to understand the new quantity and quality of information that we are generating. And I think that from my side, that's all. I will be happy to answer any question that you have later.
Thank you so much, Varun, for your presentation and for having kept the time so perfectly. Now, I would like to give the word to Dr. Csaba Ortatai from Hereditary. His presentation is about bioinformatics helping to combat COVID-19. Thank you, Csaba.
Thank you, Laura. Hello, everyone. I'm Csaba Ortatai, and I'm speaking from Finland. And indeed, I would like to talk you about the role of bioinformatics in the fight against the present coronavirus pandemic. Yeah, so I want to use some cases to illustrate also why I find it so important that people working in the R&D projects in pharma and medical sectors understand bioinformatics and how it is useful. So, as you probably know, SARS-CoV-2 is the actual viral pathogen behind the present coronavirus pandemic. It belongs to the broad family of coronaviruses, which cause multiple diseases, other diseases than the present coronavirus disease, COVID-19. For example, the common cold. And this virus, which has a positive sense single-stranded RNA genome. It is known that this novel coronavirus has actually a generally lower mutation rate than most RNA viruses. But still, what we see is that mutations, they certainly occur during the course of the infection within a single patient. And of course, when people are passing the infection to each other. So this accumulating genetic heterogeneity from the mutations, it enables the virus to adapt to different hosts and different environments. As you can expect, thousands of research groups have focused their efforts since the beginning of the pandemic in the spring to contribute to the understanding of the nature of virus and this disease. Regarding bioinformatics, it can offer assistance in two different areas, infrastructure and research tools. To illustrate the issue, please consider that today there are over 150,000 coronavirus genomes sequenced from patient samples since the beginning of this pandemic. And just to handle this huge amount of sequence data, it would be simply impossible without the proper infrastructural support. And stepping further, the sharing of research data among researchers around the world is also crucial in facilitating getting meaningful results. Okay, just a minute, I will get back my presentation. Yeah, so they have established the molecular biology laboratories and the European Bioinformatics Institute. They have established COVID-19 data portal to support the research efforts and the share and exchange of data. So this data exchange portal, which is called the COVID-19 data portal, it was set up in April, and ever since it offers, for example, over 150,000 viral genomic sequences, almost 4,000 genomic sequences of infected patients. So genome sequences from patients. 82 full data sets on gene and protein expression of human genes implicated in the virus infection of the host cells. 750 records of curated functional data on the SARS-CoV-2 proteins and receptors. 2,500 records of other supporting information, for example, COVID-19 related pathways, interactions, targets, and compounds. This will be important. And most of all, almost 250,000 of publications, which was already produced this year related to this enormous research effort. I cannot stress enough, since spring, there are over 230,000 research publications related to this topic. Just imagine the researcher community is really working day and night to pick up any kind of insight which can help to mitigate this disease. And as you can see, without this kind of infrastructural support from bioinformatics, even finding the relevant information would be impossible, because this amount of data is just crazy. But as I have mentioned, bioinformaticians do not stop at offering simply data sharing platforms or general tools. We have dedicated analysis projects and bioinformatics tools which can play central roles in the COVID-19 related research and development efforts. So in the next few slides, I will introduce you 3 groups of tools which play essential roles in the research work today regarding the coronavirus situation. There are so many tools in all these groups that I will introduce you a bit more closely, only a few to explain their relevance, just to illustrate the issue. So let's start with the tools used to assist virus detection. As you probably know, the routine detection method for the virus is based on the reverse transcriptase polymerase chain reaction, or RT-PCR, as you might have heard from the news. So this test is based on the detection of 2 genes from the viral genome, the envelope gene and the polymerase gene. So they collect patient samples and they just submit it to this PCR reaction, and if these 2 genes, the envelope gene or the polymerase gene from this virus, is present in the patient samples, they regarded that this patient sample is coronavirus positive. As you can imagine, specificity and sensitivity are very important criteria for the validity of these diagnostic tests. Specificity here means the exclusion of false positives, and sensitivity means here the exclusion of false negatives. But to have these criteria, keeping them very high, as close as possible to 100%, we need specific PCR primers which might change during the course of the pandemic, because the virus is mutating as I have already mentioned. So we have one set of bioinformatics tools, for example, this PRISET, are serving exactly this purpose: to sequence novel virus variants and to design primers with the best diagnostic value at a given time point. You have to consider that we have the so-called global initiative or sharing all influenza data, which is now playing a central role in this patient sample sequencing effort. And you have to just consider that over 1,000 novel coronavirus genome is sequenced every day. It is really mind-blowing. So because of this amount of sequence data coming into the research, the major genome sequence databases, for example, GenBank, they offer now a streamlined data submission and publication pipeline designed specifically for the coronavirus strains and genome sequences. All right. So the second big topic where bioinformatics have substantial contribution to the tracking is the tracking epidemiology and evolutionary analysis of the virus genome. So previously they identified and sequenced the genomes. The second group of tools is for observing what is changing, where the mutations appear, how they affect the disease and the virus itself. So these analyses serve multiple purposes. For example, calculating different epidemiology parameters, such as the R0, what you have perhaps heard about, which is the number of average number of infections caused by an infected individual. So it has to be calculated for a given country or town at a given time point to track the efficiency of different administrative measures. So these are basically mathematical epidemiological models which are essential for monitoring the situation. For example, for forecasting the need of hospital resources in a few weeks' time, and at the end of the day, to guide political decision making. So as the pandemic progresses, as I've already mentioned, the virus is naturally accumulating mutations, and tracking these mutations geographically and time-wise, we have to do this to have a better understanding about the dynamics of this disease. So there is a very interesting tool called Pangolin, interesting name choice, and it is for visualizing the spread of different virus mutations and lineages geographically. I've seen several studies and articles using this tool, and similar images what you can see on the screen. These images are even appearing in the news. For example, I've seen this on BBC or the Guardian. As I've mentioned, these over 150,000 virus isolates sequenced during the past 9 months, and there are so many mutations observed in the virus genome that some of these mutations are changing the infection behavior of the virus itself. So based on these mutations, the individual isolates can be identified, tracked geographically, and they can be grouped into strains and identified groups. On this image, you can see the different colored branches of this tree. They are representing different strains with different mutations. Okay, so what we can see here on this view, that in the United States and South Europe, the G and the GH groups are dominating this disease. Those are the main strains spreading, while in Northern Europe and Far East, the so-called GR group is much more prevalent. Actually, the same kind of results were published just a few days ago, where researchers find different virus groups in different continents. You can see that the different groups are dominating for differently North America and Europe. That's a very, very dramatic finding, because this might be the first step towards understanding why this disease behaves so differently in the different countries. All right. Finally, probably the most useful, or for you the most interesting group of tools are the ones which are assisting drug design projects, because understanding the molecular mechanism underlying the disease pathogenesis is key to identify potential drug candidates for clinical trials. So viral host protein-protein interactions play a crucial role during viral infections and hold promising therapeutic prospects. And actually, nowadays, the most common approach to develop antiviral drugs against coronavirus is drug repurposing. So in drug repurposing, known and already approved drug compounds are screened if they are affecting the protein interactions between the coronavirus proteins, such as the infamous spike protein and their receptor molecules on the host cell. Since multiple drugs are already developed for other coronaviruses, especially the one caused earlier, the SARS epidemics, here the use of computational approaches are very common, and there are many such tools. but usually these approaches, modeling approaches, are coupled with database search approaches. And the last example I would like to show you is exactly that. So it is called the Corona Drug Interaction Database, or CORDIT. This is one is from a German university in Marburg. It is automatically screens and process relevant publications and critical trials to identify drug candidates. And right now they offer data for over 770 drug compounds. And experimental and researchers are screening these drug compounds if they are indeed helpful. So bioinformatics is great with open source software, and as you have seen, the power of community-based research came out beautifully in present COVID pandemic. So researchers, software developers, data scientists join their skills and resources to offer a wide range of options and the solid base of that data and knowledge for the medical professionals who are working tirelessly to fight against this novel viral infection and all of their consequences. So thank you for your attention, and I give back the word to Laura. Microphone.
Can you all see me?
Yep.
Yes. Sorry for that. I'm very thankful. Thank you, Trevor, for this interesting talk. And now I would like to give the word to Dr. Dimitrios Doutsinos from John Radcliffe Hospital of the University of Oxford, who has joined us and will talk about application of bioinformatics in cancer patient treatment. Thank you very much.
Hello all from very cloudy Oxford. Thank you very, very much for inviting me to speak to this event. It's exceptionally exciting, and to basically see what bioinformatics can do in clinical practice, and to have a look at what the next steps can be in order to make patient care even better than it is now. Unfortunately, there we go. So yeah, these are my slides. So I'll be talking about bioinformatics in oncology and what I've been involved in so far, and 3 or 4 projects that might be showcasing how we use bioinformatics in close to the clinic. Now, very little bit about myself to begin with. I came from Greece and moved to the UK at a very young age, where I undertook all my formative training, including clinical work and an MHRA certification in clinical trial design and regulation at Imperial College London. Upon which time I moved to France, where I carried out oncology research in neurogenetics and neuro-oncology, where I worked on proteostasis and glioblastoma in particular, developing more preclinical models of disease and disease heterogeneity. And this led to some computational biology and in silico drug design work in Sweden, as well as some biomarker discovery work with INEOS in Athens. And upon that, this culminated to my current position in translational oncology at the surgical department, the Department of Surgery at the University of Oxford and the Oxford University Hospitals NHS Trust. Now, the main reason why I did this whistle-stop sort of overview of my background was not so much to give you an example of what I've done throughout my career, but to pinpoint all the variations, all the huge heterogeneity and collaborative effort that goes into patient care, from clinical work to clinical trial design, preclinical models, omics interpretation, translational medicine, and drug design. Now, all of these should directly input feedback into patient care, but instead what you really get is just a really complex mix of data So huge amounts of information, but how are we actually going to translate that into diagnostics, prognostics, and treatment, be that patient care in terms of regulations or actual drugs? Now, this is where bioinformatics comes in, and this is predominantly why why there is so much onus put on bioinformatics, and especially in oncology, because despite huge advantages and advances in patient care, we're still being hampered by intra and intra-tumoral heterogeneity and a lack of nuance in specialized treatments. So all the information is there, and more is added constantly, but translating this into drug repurposing, off-label prescriptions, diagnostics, prognostics, bench to bedside translation, biomarker discovery, and mutational or omics drivers of disease is incredibly difficult. However, there are some very interesting projects that are currently going on that are translating these data into diagnosis, prognosis, and treatment selection, and I'd like to go through a couple of those with you now. Some of these have been done in collaboration with INEOS, and as far as I'm aware, you'll be able to go into more detail during the workshop later, which will be fantastic for you. Now, the first example will deal with a third of what we spoke before. Obviously, treatment selection, diagnosis, and prognosis are all interconnected, but I've broken them down in three examples in order to aid discussion afterwards as well. So, classically in the clinic, you'd have a couple of melanoma patients. They will come in with a nodule, and then after a standard medical history and physical exam, the physician will decide to follow up further, and then there might be a skin biopsy and resection, followed by histology, and in some cases carry out whole exome sequencing or microarrays on the sample. Now, all of this information does inform treatment up to a certain point, because of the regulations that are in place. All patients with melanoma will get a particular treatment according to the genetic background. Now, putting these through a VCF analyzer, particularly for cancer, will give you particular SNPs or mutational load on each patient. And if we take this particular example, patient A, for example, would have mutations in particular genes like TERT, BAP1, and BRAF, among others, and patient B would have some mutations on the gene NRAS. Now, putting these through a computational app that decides whether genes are prioritized or not according to their importance and their activity in terms of biochemical pathways, we can actually wean a lot more information out of that. So patient A, we have the TERT mutation and the BAP1 mutation, which points to a genetic predisposition. Now, whether the patient actually does have a particular type of melanoma or not, this is very helpful because it can aid medical history. We can actually look back, and also genetic counseling for their children or other members of their families. Then they also have a BRAF mutation, which points to a particular subset of therapies that are very well documented, like dabrafenib, encorafenib, vemurafenib, and others. Now, patient B is more tricky. They have a mutation in the NRAS gene, which means that there is no targeted therapy, but at the same time, there are studies that show that you can treat that with MEK inhibitors, second-line chemotherapy, or immune checkpoint work. Now, of course, one of the biggest problems that we've got in oncology is that sometimes patients become treatment resistant. The tumors are too aggressive and they come back, and then the treatments no longer work. Now, that extra bit of analysis gives us prioritization of genes within these subsets of altered mutations, and gives us clues as to what further drugs we can use off-label or drug repurposing, like we spoke about before. So in patient A, in this particular example, there were mutations in the DMD and ERBB3 genes, which are involved in lipid transport and cell-to-cell interaction, which points to a potential involvement of the mTOR pathway, and therefore we could potentially prescribe rapamycin or dasatinib In patient B, Notch1 signaling and with systemic processes involved in cell differentiation, which means that a therapeutic alternative could be an experimental drug like GSI RO492997. Now, of course, that does not mean that any of this is a substitute for diagnostics or clinical care, but it provides very, very pertinent information as to what could be a potential alternative for patients that the conventional therapies do not work. Now, the second example is on patient stratification, because as we spoke before, a lot of the time we give patients the exact same treatment, and obviously every single person is different. So it's very, very pertinent to use particular types of therapeutics in particular groups. And this is also a very good example of bridging very basic research with clinical work and clinical samples, so sort of bench to bedside and back. So in this particular example, in glioblastoma, which is a fatal brain tumor, we had the transcriptome of cells, preclinical models of GBM. And putting it through a very similar pipeline, we found a lot of hub functional genes constructing a signature of behavior of the tumors according to a master regulator biochemical pathway. Now, putting these through public databases and independent brain cancer cohorts through a neurosurgical unit that we were working on in France, we were able to sort of stratify patients into 4 distinct groups. This is particularly important because on top of the mutational load that we know exists in glioblastoma, we had an extra stratifier to make sure that if particular clinical trials happen in the future, we'll be able to actually stratify patients better. Why is that important? Because if a clinical trial does happen and it fails, then we're able to do the meta-analysis on it, or even better, we give different therapeutics to different arms of the trial, which means that we're going to have more meaningful results out of the trial. This particular study gave us more defined treatment groups, and it's a verified method of selecting a particular inhibitor therapy for patients suffering from cancer, and this inhibitor was against that master regulator that we spoke about before. Now, the next example is a truly fantastic initiative that is happening across the UK at the moment, but I am pinpointing the fact that Oxford University hospitals are participating in it because in September on September 3rd this year, our pathology department became 100% digitized. So bioinformatics, of course, can be involved in both omics, so transcriptomics or gene signatures or genomics, but a huge other side of it is imaging. And what this PathLake initiative is trying to do is digitize cellular pathology. So we're trying to do that across the UK, and in particular in Oxford, we achieved that 100% digitization this year, which basically builds an annotated pathology image, which is called the data lake. And this is fantastic because you can have rapid referrals, so pathologists within hospitals can work in sync. Diagnosis can become a lot faster, and you can have a lot better lab workflow, and also an instantly available remote consult, which of course, even in a time of a pandemic, is very, very important, because the pathologist may not even have to be in clinic in order to actually look at the results and make sure that the diagnosis is accurate. Now, on top of that, we are developing artificial intelligence tools through machine learning in order to have faster diagnosis and guided therapy. So you could have immunohistochemistry biomarker detection and scoring like HES6 and Ki67, deep learning neural networks and machine learning on identifying cellular characteristics in order to have signatures to diagnose patients. There have already been studies, especially here because we're a prostate cancer center, when advanced and indolent prostate cancer glandular architecture can be recognized through these whole slide imaging advances, and then through supervised and unsupervised digital image analysis, we can have a sort of oncology and pathology integration to make the best decisions for the patient upon diagnosis. The last example, which kind of bridges everything really that I've been speaking about so far, is spatial transcriptomics. The previous project was headed by Professor Claire Verrill. This particular one is headed by Dr. Alistair Lamb, who's a surgeon and the lead of robotic surgery here at Oxford. And they're trying to do spatial transcriptomics on tissue slices, where it involves sample preparation, imaging, a sort of barcoding and library preparation, which is then sequenced, and then you get a data visualization. So, you know, a normal section would look like this, but with spatial transcriptomics, you're effectively figuring out where exactly on the slide and where exactly in the tumor you have genetic and genomic drivers and alterations to aid diagnosis and particularly prognosis. So in this case, you could be combining immunohistochemistry and gene signatures, therapy efficacy prediction, can find drivers somatic mutations in benign samples. So for transurethral, for example, prostatectomies, we can prognosticate and monitor a lot quicker because a hyperplasia could become cancer, but it's not diagnosed early enough. And then we can also talk about and look through other factors of carcinogenesis like immunofiltration and angiogenesis, and also we build information on intra and intertumoral heterogeneity. Now, these are just a couple of examples of what we're currently doing, but essentially I hope that it has been pretty clear that there are many important factors that contribute to clinical care, but through bioinformatics, we can actually make the connections, connect those dots, and through diagnostics, treatments, and prognostic procedures, actually make clinical care a lot better and reach further towards personalized medicine. So thank you very much again for inviting me. I hope it has been informative, and really looking forward to the discussion. Back to you, Laura. Thanks very much.
Thank you, Dimitris, and thanks to all three experts for your valuable input. And now I would like to start the Q&A session with the first question for Farhan. Farhan, what is the level of expertise that you think medical doctors need regarding next generation sequencing technologies, genetic risk prediction, or bioinformatic analysis?
Yes, here I am. Thanks. This is the $1 million question, I would say. And I admit opinions. My opinion, and from my, I'm not a medical doctor, I am a biologist. My opinion, after some experience of being in some medical discussions about some patients, me always participating from the genomics side, is that we need some training for medical doctors, at least what they I think, is to understand the basics of these technologies, or if not the basics, the possibilities. The possibilities. We need to understand when they are useful and when they are not. Some patients could complain. So now the patients, well, all of us, we are patients sometimes. As patients, we have access to an incredible amount of information, and we can post very challenging questions for medical doctors, as why you are not sequencing my exome. No? I know someone that they sequence the exome and they discover the origin of this disease, and then they had genetic counseling for the next child, and blah, blah, why you are not sequencing my exome? Well, and what we are trying to do in the BIOS is explaining when it's useful sequencing an exome and when it's not. So I would say that the training that they need, of course, they can go forward and have more in-depth training, but at least they should have basic training to know, if not the basics, the potentiality, the capability, the new horizons that we are opening with these technologies. Because as I have said in my talk, the paradigm has completely changed. What was almost impossible in 2000, now it's done in less than one week.
Wow. Great, thank you so much. And now I have one question for Chaba. Here it comes. Can genomics help me as a patient in a coronavirus infection? If my doctor knows my genome sequence, would it help me as a patient?
Well, yeah, thank you, Laura, for the question. The answer is a bit mixed. So I would say that it wouldn't be the best tool to help a patient. But in some cases, we know that there are certain genomic variants which are associated with more severe symptoms. And I think that at least screening for those variants could at least inform the doctors what kind of outcome they should expect, or how severe a disease progress they should expect. So I would say that not a full genome sequence, it wouldn't make much sense, but at least screening for some of those known variants which are associated with different outcomes, that would make sense. That's my personal opinion.
Thank you very much. And now we received one more question in the chat, and here, I think this is also for you, Chaba. What is the credibility of the GISAID bioinformatic tool for SARS-CoV-2?
Well, I would say that there are so many tools, and if you might be able to see that I have basically cited these tools from a review article, and there they try to collect those tools which are reliable and credible. So we have to keep in our minds that this from researchers' point of view, this all development has happened in an incredibly short time. So there are many things which are based on assumptions, but I would say that those tools what I have cited or shown you, those are from credible sources. That's my personal opinion.
Thank you very much. And we have another question for Dr. Docinos. How can bioinformatics and AI algorithms cooperate to contribute to patients' better healthcare solutions as the regulatory framework is very strict?
That's a fantastic question, and it is becoming an incredibly complex field, because, of course, it is something that it's constantly evolving, and it's not currently fully documented by health regulatory authorities for getting such tools through to the clinic. However, there have been certain distinctions between how the use of these tools are actually allowed, and I don't know if it was clear enough from what I said before, but a lot of the time these are purely advisory. So it's not like these pieces of information, these AI algorithms, these bioinformatics outcomes are being put forward as the be-all, end-all diagnostic or prognostic tool that will determine a treatment therapy for a particular patient. They will be used alongside the vast experience of every clinician that is working with a particular patient to help out the diagnostic process. And so far, if an AI algorithm or a bioinformatics app is designated as such, is much more easily regulated because it doesn't fall under a Class 2 regulatory approval sort of bioinformatics tool. So they certainly can cooperate to contribute to patients' better healthcare from an evidence-based perspective as well, because if we think about the fact that we have huge issues with sort of interpatient heterogeneity, then if these algorithms are being put to the test and they, again, in a sort of advisory capacity, and they seem to work and be able to sort of distinguish from one patient to another, then they will become a lot more mainstream, and then of course that will lead to us being trained properly in order to use them in everyday clinical practice. Of course, this will still take a bit of time because it requires extra training by the clinicians and extra sort of integration of these techniques within hospitals, but these things do happen, and we see it very well with PathLake, because you've got industrial collaborators as well as universities and hospitals coming together to produce projects like these, where you have big repositories that will help with AI and bioinformatics. So yeah, I hope that answers your question.
Thank you very much, Dimitris. And we received another question in our chat from Elena, who is a medical doctor and now studies her master in bioinformatics. And she's interested in Bioinforminer. She says, I wanted to ask if this software app available for if this is available for hospitals to buy, so a bioinformatician can work with it. And in the department, for example, in oncology?
As far as I'm aware, yes. And I don't, Eleanor, I don't really know whether you're going to be attending the workshop later, but there are, I think, quite a few representatives from INEOS, as well as myself, I suppose, within this group. So please do get in touch to have more sort of in-depth answers to these questions. It's certainly something that would be quite useful to have in the clinic. At the same time, of course, you will need the appropriate infrastructure in place in order to be able to handle the clinical data. So as long as the sort of clinical regulation within each hospital and data protection is in place, then absolutely, it could well be that you are able to use Bioinforminer and other such apps like the VCF analyzer within a hospital to analyze clinical data.
Thank you so much. So Elena, you're welcome to stay for the workshop. Happy to see you there. And now I have one more question for Faran, which is, can we just rely only in bioinformatic analysis to make a genetic diagnostic in one patient?
Well, I would say it depends on which bioinformatic analysis have you done. Okay, for example, with my students, I do one exercise. I give them exome, the data of a whole exome of one individual, and I ask them please to identify probably causal mutations for a disease, and they identify many loss of function variants. So these variants introduce, for example, a stop codon in a protein, and they realize that this individual has many stop variants, and then the bad news I give them is that all of us, we have maybe 100 and 20 of them in homozygosis stop genetic variants in our genome. So in this sense, bioinformatic analysis would not be enough if bioinformatics is just this. But when bioinformatics integrate information from other patients, for example, and we realize that these mutations are quite frequent in the population, we can say, okay, this is stop codon, but this never will produce an important disease. So in this sense, when bioinformatics is quite huge and wide, I would say can be enough. But when this is a mutation that you discover for the first time, I would say then this is not enough. Even if it's in a gene where other patients share a mutation causing this disease, bioinformatics needs the next step, that it's functional validation. Okay, and then what we need to do maybe in some model organisms or some in vitro analysis to confirm, to do the functional validation that this mutation is really generating the disease. So there is not a single answer. In some cases, I would say bioinformatics is enough when we integrate many types of information, especially from other patients. But in some and in diseases, this is important because many times we discover by the first time a mutation in a patient. We need even more. We need in a new gene that has never been related to this disease. We need to do some further experimental validation experiments.
Okay, thank you very much, Ferhan. And now one more question for Csaba. Artificial intelligence is a big thing in recent years. Is it used in bioinformatics, and is it used for the coronavirus-related R&D?
Well, yeah, again, the answer is yes and no. So you might just heard in the news that they used artificial intelligence to assemble protein structures from sequence, which was really a big bone, and people were working on these kind of issues for decades already, I would say. So this is a huge step forward, and that will be certainly a big help. But in general, I would say that artificial intelligence has its place in R&D, but I believe that right now it won't play a big role in the research work and development work in the coronavirus situation, because these tools are so new that they won't find their place in the research and development infrastructure by hopefully this pandemic will end by that time, soon, in a few months' time. That's what I think.
Thanks for your view on this topic. And Dimitris, I would like to give the last question to you for this Q&A session. From a patient point of view, what is the main advantage that a clinic I attend is using these bioinformatic tools?
I'm so sorry, could you repeat that?
Sure. So it's from a patient point of view, what is the main advantage that a clinic I attend is using these bioinformatic tools?
Predominantly information, if I'm honest, because looking at it from a patient perspective, especially in oncology, and I'm sure in many other fields, you know, hearing that C word as soon as you get through the door, basically everything blurs into the background. You know, whether it turns out to be benign or not is quite a stark sort of emotional strain. And the more we can actually tell patients about their outlook, about their outcome, about how much time they've got with their families, or about the possibilities of certain therapies working or not, the better for them to be able to make informed decisions. Because of course, what we do, both biologists and medics, what culminates in the clinic is not just about the disease; it's about the patients and what sort of revolves around them, including their quality of life, because it's not just about extending life; it's about making their lives better, and how to go about it. So tools like these make sense of the clinical problem, because currently we can either treat the symptoms or have, albeit fantastic, advances in therapeutics. However, these do not work for everyone, and understanding a lot more is certainly something that that will be advantageous to patients. And a lot of the time, and we see it a lot across the world, and especially in the UK, that a lot of people are actually, a lot of patients rather, are very involved in charity. So what they want is for efforts to be made for the future, for future patients or future parts of the population to have a better outlook, to have a better life, and that translates also to the next generation. So if we do have better tools about predicting disease, then we catch it earlier, we make the prognosis a lot better, and so on and so forth. So.
Thank you very much, and I think this was a nice summary and like a repetition for all of us why we are doing this, project, and how much impact it can have. So, and with this, I would like to thank all three experts having talked here and having responded to the questions. As I said earlier, if you as a participant would like to know more about it or post more questions, then just go to our website or write me an email. And with this, we are moving to the next session, which is the session on the BioS project outline. Yes, and I would like to start with my presentation. Here it is. Thank you very much. About the BioS project, our major aims and objectives, and the partners and experts involved. Next slide, please. Or thank you. Yes, this one. So we started our work in January 2018, and we concluded by the end of 2020. So there are 3 weeks left. We have 13 partner organizations from 8 countries across Europe. We all come from different backgrounds and sectors, either the educational sector, the healthcare sector, or we have a background in bioinformatics. Next slide, please. As coordinator, we have Steinbeis University Berlin. From Greece, we have Indius Application, Olympic Training and Consulting, the University of Patras, as well as Guybridge Partners. From Spain, we have the Bioinformatics Barcelona Association. Belgium is represented by the European Medical Association. Further German partners are the European Recreation and Health Valley and BG Clinic Mona. In Italy, we rely on our partner 4, and in Portugal, on the Vocational School of Alta Lima Epalima. Hereditary has its office in Finland, and last but not least, we cooperate with our partner in Cyprus, the German Oncology Center. And I think this is a really good opportunity for me to thank all partners for their contribution and their hard work in the past 3 years to make this project a great success. And this was possible thanks to our diverse competencies, which we all bring to the table. So designated tasks are and were project coordination and communication, quality assurance and evaluation, dissemination and exploitation of project results, but most importantly, the development of our project core element, the open online course in bioinformatics for healthcare professionals. Next slide, please. So my colleagues will talk about our core result in much more depth. So here I would just like to outline our major objectives. With the BioS online course, we aim at advancing the skills of European medical doctors and other healthcare professionals through the development and delivery of new modular vocational curricula on digital skills and computational biology. The creation and conduction of the BioS course allows us to tackle concurrent challenges in European healthcare systems, services and policies with the ultimate goal to improve healthcare services for European citizens. In the BioS course, participants learn how to use genetic information services for their daily practice with patients. Next slide, please. BioS follows a waterfall methodology for the preparation, design, and delivery of the training program. As I said, my colleague speaking after me will give you much more information on the BioS course structure, content, and impact. But as you can see here in the little graph, we started our work by the design of the BioS curriculum, the certification scheme, and the assessment procedure. This so-called work package was followed by intensive work on the development of the BioS educational material. And more or less at the same time, we started the creation of the virtual learning environment where we have put this BioS course. And then the last stage was the delivery of the training. So in our work, we were also supported by an external advisory board, which is composed of experts in the healthcare, bioinformatics, and that sector, so vocational education training sector at European level. And this external board gave us advice and feedback, and they will help improving the quality of our deliverables significantly. So at this point, I would like to thank once again all experts involved for their great work and contributions. And with this, I already conclude my short introduction to BioS, and I would like to hand over the word once more to Farhan Kasal, giving us insights into the content and structure of the BioS learning material. Farhan Kasal did not only support the creation of the BioS training material, but he's also one of our teachers in the course. So thank you very much, Farhan.
Thanks again, Laura, for the introduction. Well, hi again, I'm Ferran Casals from Bioinformatics Barcelona, and now I will briefly explain you how these materials were designed and how are organized. In fact, I have seen that many of you or several among you have already participated, so I will try to do it short and interesting. It's always the best combination, okay? So, well, importantly, these materials are accessible in all the languages of this consortium. And they are organized into modules. This is very important, okay? The modular organization, meaning that you don't need to go through all the modules. You can take the module that you need. It fits better to your interests or to your needs, okay? Here you have the 4 modules on basic bioinformatics, computer, statistical, statistics, no, for medical, for physicians, personalized genomics, and quality improvement or communication in healthcare. As Laura has said, we had the advice of an external academic committee that was made up of members from different groups, from medical doctors. This is very interesting since they are our main target. We needed their advice to design interesting materials for them, bioinformaticians, and experts in online education. We had 2 meetings with them in Barcelona, one at the very beginning while we were designing the materials, and once we agreed on how these materials should be organized, we had the next meeting in I think it was in 2 or 3 months to discuss about the progress of the materials. Okay, so as I have said, the modules are organized. The course is organized into 4 modules, and all of them are organized in the same ways. They are organized into weeks. It's very important, this organization, because the participant knows exactly how long, the amount of time that he will need to dedicate to each one of the modules of or the weeks. 3 of the modules are longer, are 4 weeks. The last module is only 2 weeks with a total dedication of less important than the others. So the activities are exactly of the same type. So across the different modules, we find always the same type of activities. And here, the video lectures are very important. We have 2 video lectures per week, and the rest of activities, clinical cases, debates, weekly quizzes, problem-based learning, short exercise also, are based on the video. So first you take the video and then you go to the exercises. We have 2 videos of about 8 to 10 minutes per week, meaning that we have 8 videos per module, plus and a very short introductory video of an interview to an expert in the field per module, so that it's 9 videos per module. So more than going to see all of these modules, what I'm going to do as an example, because as I have said, they are organized very similarly, we're going to visit how is organized module 3, personalized genomics in patient care to give you a general idea of how the materials are organized. If we go, well, we see here in this slide, no, once you are in the course, you can go to the module you like more. And then once you are in the module, you can see the different weeks, the overview with the interview to the expert, and the 4 weeks. Okay. Then, for example, we go now to the last week. This module is quite wide in the sense that we start with very basic genomics, and we finish with more complex situations, like the situation I was saying before, which is the genetic test I should perform to have a diagnostic for this patient. So I would say it's a quite ambitious module, starting from very basic concepts in genetics to current needs of some researchers or medical doctors. So let's go to this 4th week. And once we are there, okay, we can see the 2 videos here. Let's go to the first video on nucleotidic variants. Okay, we always help the participant to know where we are. Now we are in module 3, week 4, video 1, and all the videos have been recorded and designed in a very similar way, with always stating the title of the module, the week where we are, in this case, diagnostic tools, how to select the correct test for, and in this case, the first video on sequencing. And then always at the very beginning, we have the learning outcomes. It's very important that the participant knows what we expect, no, in the next minutes, or what we want to explain in the next minutes. After this, the presenter is always assisted by different types of animation, the whole screen or half the screen, some subtitles in some cases, some very short videos to show activities, like in this case, analyzing data from a sequencer. And at the end of the video, we have a synthesis of the key ideas that we want the participant to take home from this video. So I have said all the 30 videos in this course are structured and designed in the same way that this one I'm showing as an example. Okay, once we have seen the video, and in this case it was the first video of one of the weeks, we have a short activity. In this case, and I have taken this as an example because it's quite interesting how the participants will learn to manage directly this sequencing data. So we take some sequencing data from some anonymous individuals in these projects, like the 1000 Genomes project. We take this data, we prepare the data to be small enough to be able to be loaded in a computer, and they learn to use IGV, in this case, the tool that all of us, we use to visualize this data. So we want them to feel comfortable in this environment, first with very basic questions on what they see in the browser, as how many genes I see here, 1, 2, 3, do they have exons, they have introns, just to feel comfortable into this environment. And then once they upload the data of the patient, we ask them to identify mutations. For example, in this case, we have the offspring that has inherited this mutation present in the father, but not in the mother. Okay, so looking at this information in IGV, this browser, they can fill the table you have seen before, where we are asked for genotype data for these individuals. Okay, after that, as I have said in my talk, we have genetic variants, but we have to make sense of this genetic variation. Sometimes, most of the time, I would say this genetic variation is neutral, and we want to identify the variation that it's not neutral, that can be related to disease. So what they do is like a simulation of what we do in the labs, that it's the functional annotation of this variation. For doing this, we use the Ensemble database, one of the most popular databases we have in genomics, not only for human genomics, also for other organisms, and they use the variant effect predictor. They upload the same file they have visualized in IGV, and they get the results, and then they got a series of questions about the results. So this is what they get. And then we ask them, well, okay, how many of these genetic variants are coding? So they are in genes. Are they producing a change in the protein? How many of them can be pathogenic? Okay, so they need to explore the results in the graphs or in the table to understand and to summarize the information they are getting. Note that in a simpler fashion, they are doing what we do in the labs, so that it's visualizing the data, then annotating and trying to make sense of all this data. This is one exercise that it's supposed to take about 1 hour for the participants. The activity after the second video usually takes longer. After the the 2 videos and the activities, they can have a quiz. They can go to a quiz with 10 questions. Like it's like to check, no, if they have if everything is going okay, no. So it's like a self-evaluation quiz that they can take. And finally, they can also perform other self-assessment activities with more complex exercises where they can access to the solution to see if they are able to do by themselves. Once they feel comfortable with all that, if they want, they can move to the evaluation to accreditate that they have participated in the course. And that's it. I hope that with that, you understand better how this course is organized. Thank you, Laura.
Thank you very much, Ferran, for your presentation. I think it became very clear what is the content of our course. And now I would like to give the word to Christoph Silaki from Skybridge Partners, talking about the development of the virtual learning environment. Thank you very much, Christoph.
Dear Laura, thank you. Good evening, everyone. My name is Christoph Silaki, and I work as a researcher at Skybridge Partners. The Biospiritual learning environment offers the vocational open online course, Introduction to Bioinformatics, for the medical and healthcare professionals in 8 languages, namely the English, German, Spanish, Finnish, French, Greek, Italian, and Portuguese. It is a form of massive open online course, but focused on vocational training, taking into account the VET teaching and learning particularities. The learning and assessment material is offered as open educational resources under Creative Commons Contribution Non-Commercial 4.0 International License. It also creates a virtual community to support interactions among learners, instructors, and teaching assistants, and the users can meet, exchange experiences, and participate in group activities through the discussion forums. As of December 2020, the BioS virtual learning environment has more than 1,000 registered users. The massive open online courses constitute one of the most powerful and engaging tools for open and distance learning, the MOOC approach. It allows the registration, open access, and remote participation for a large number of participants at the same time. It can also support a large-scale interactive participation, combining the traditional course materials with audiovisual content and providing user forums that can help build a community. It also promotes the micro-learning as it allows the trainee to show progress efficiently in a short time frame. It can also support a learner-centered training model that promotes the creation of an active and stimulating learning community. The learning platform used for the purposes of the BioS MOOC is Openidx. Openidx is an open-source learning platform that was created in 2012 by Harvard University and the MIT for the one of the biggest online learning portals in the world, the edx.org. We have selected the Openidx technology for the BioS VLE because it is an open-source platform on which we can build to cover the learning challenges and needs that are actual today. The main features of the Openidx platform are summarized below. It is an open-source learning platform. It is designed for the MOOC world of an online and self-paced learning. It caters nicely to a larger scale audiences. It has an interactive forums and discussion boards. It can work on any device. It offers interactive content with adaptive video streaming. Moreover, it can provide intelligent learner-centric analytics, and there is also the ability to integrate multiple third-party systems and tools like SCORM, LTI, and iframe. Since the Openidx is an open-source platform, it was modified, and the BioS VLE was developed tailored to the training needs of the BioS target groups. The BioS VLE user interface offers a brief course outline that helps learners see the full scope of the course contents, and it also facilitates them to return to the last content area they were viewing. The course is structured in a modular manner and is organized in sections, modules or weeks, and subsections the lessons. This is in line with a relative new microlearning concept in which the content is broken down into bite-sized pieces of learning material. Instead of long-hour lectures, the BioS online learning modules are built up for many bite-sized components of short videos, maximum to 10 minutes long, and individual exercises. These components are as modular or standalone as possible, since the modularity has many benefits. The BioS VLE is developed with an active learning theory at its core. The acceleration of active learning comes through its modularity. The learning modules are organized so that the video learning material alternate with exercises. A typical learning sequence has a video lecture followed by quick exercise and so on. All BioS lessons use videos with interactive accessible transcripts available in 8 languages. The BioS Media Player displays caption files in an interactive sidebar that benefits a variety of learners, including learners who are hard of hearing. The BioS VLE also provides many different types of problems and feedback options that can be used when designing the exercises and assignments for the BioS course. The multiple choice, checkbox, or drop-down problems have a limited number of possible answers and can allow the learners to quickly check their understanding in the middle of a learning sequence. Moreover, the open response assessments allow the instructors to assign questions that may not have a definite answers or may be too lengthy for the instructors to grade at a scale. They can be designed in 3 ways: as peer assessment, self-assessment, or staff assessment. The learners can submit a response to the driving questions, and then that learner and their peers can compare the response to a rubric that you create. This type emulates the classroom experience for the learners of the BioS online course. Any out-of-the-box problems, such as the multiple-choice problems, can be graded or ungraded. The BioS course team has a complete control of what type of graded exercise the BioS course will have, how much exercises count to the final grade, and when they are due. The Instructor Dashboard provides a source for tracking students' progress. The final grade is calculated based on 2 categories. Firstly, the score obtained from the practical quizzes. In total, we have 13 practical quizzes throughout the 4 learning modules, and also the score obtained from the final exam quizzes, which consist of 4 final exam quizzes, 1 per learning module. Each category contributes to 50% in the final grade. The passing threshold of the course is also set to 50% of the final grade. Every learner who reaches or surpasses this threshold will be given credit in the form of a certificate of course completion. The certificates are configured through the BioS Platform Studio and are automatically issued when the learner meets the predefined criteria. In addition, all the BioS successful learners can claim their certificates online through the progress page as soon as they pass the predefined threshold. As of 16 of November 2020, 95 certificates have been issued to the successful BioS learners. To effectively communicate with the BioS learners, the discussion forums have been added, and these allow the learners to share their opinions and ideas and engage into conversations. Another way to communicate is through the bulk email functionality of the platform. Upon the successful submission of a message informing that the email was was sent is displayed. The email body can be formatted and managed through the BioS easy-to-use text editor. In addition to the course updates, there are an alternative and great means of communication. During the BioS MOOC, any important date, schedule changes, or announcement of a specific activities was delivered through this functionality. After learners have read a message, they can dismiss it. From a technical point of view, all the updates are using HTML for formatting and styling. To increase the active participation of the enrolled learners, we have organized live online consultations, and learners had the opportunity to meet online the BioS instructors and discuss with them about any aspect of the BioS material. For this reason, a live video conferencing system was developed using the HTML5-based open source application Big Blue Button. We have selected the Big Blue Button because it is an open source, and thus we could further customize it to meet the BioS learning needs. It includes a complete set of features and integrations for instructors and students, such as audio-video, multiple webcam sharing, and many other features. The live video conferencing of the system is available in the link that you can see on your screen and was successfully used during the BioS live versions. Before rolling the course out, the platform has been extensively tested by both the BioS staff internal evaluation and the end users external evaluation. Firstly, the BioS staff members evaluated the platform and the online courses in 2 rounds. In the first round, the English version of the BioS MOOC was tested. In the second round, the 7 different language versions were also tested. The diagram below shows the evaluation of the platform. And you can see the responses we received for the question, how would you rate the level of the BioS MOOC, using a rating scale from 1 for the very poor to 5 for meaning very good. All the technical aspects encountered during the pilots were reported in a document, and our technical team made improvements and fixed the issues reported throughout this test. Later, the external evaluation took place. Healthcare professionals, medical doctors, and educational experts pilot tested the platform and all courses. In total, we received 21 responses, but these were received in total 19, since 2 experts sent twice evaluation forms, as you can see in the first diagram. The second diagram presents the responses received for the question, how would you rate the level of the BioS MOOC, using again a rating scale 1 for very poor to 5 for very good. It is important to mention that 52.4% evaluated the level of the platform as good, and no one evaluated the platform as poor or very poor. Throughout the pilot, several improvements of the platform were proposed by the external experts and were prioritized according to the potential for usability improvement, and were implemented by the technical team of Skybridge. Analyzing the end-user responses to all the evaluation questions, the end-user satisfaction during the pilot phase reached 97.35%, which gave us the green light to roll out the courses. Each time a learner interacts with the BioS platform, relevant data records are created in the BioS VLE data storage system. In addition, the following reports can be downloaded in the form of CSV files through a dedicated data download page accessible only to the staff members. These refer to the profile of users, list of answers given to some specific problems or assessment, list of certificates issued if applicable, grade reports, and these reports in general are available for download through a web link generated in the platform. To keep the student data secure, these web links cannot be saved or emailed, and the copies of the links expire within 5 minutes. About the visitors' satisfaction, it was measured using a post-course survey throughout the G Suite integration. Based on the feedback we received from the learners, several improvements were made to the platform. As of October 2020, the visitors' learners' satisfaction is 96 0.16%, and we are very happy for this achievement. In a few days, the BIOS project will be completed. However, the end of the BIOS project is a new beginning for the BIOS virtual learning environment. The BIOS VLE will be improved, taking into account the feedback received from the learners during the course delivery, and the refreshed version will roll out on the basis of a Memorandum of Understanding and the commercialization agreement for the BIOS partners. Thank you for your attention.
Thank you very much, dear Krisa, for your input. This was very interesting. And now I would like to ask Elias Konstantinopoulos from the University of Patras, outlining the BIOS course delivery. Elias, the floor is yours. Thank you.
Thank you for the introduction, Laura. Good afternoon, everyone. My name is Elias Konstantinopoulos. I'm representing the University of Patras team for the BIOS project, and I'm going to talk to you about the delivery of the BIOS course. The course delivery comprises the stages presented to you by the partners before, namely the design and the development of the educational material and the BIOS VLE. The first important goal of the BIOS course delivery was to attract potential trainees and invite them to attend the course. Beside the course announcement through posts in social media and relevant websites, the BIOS staff performed and still performs persistent contacts to individuals as well as associations. Promo material, which included posters, leaflets, and bookmarks with the QR code linked to the BIOS MOOC, were persistently delivered. The course was delivered, is available in 8 languages: English, German, Greek, Spanish, Italian, Finnish, French, and Portuguese, and its delivery took place in 2 rounds. The first round commenced on the 3rd of February 2020, and the second round commenced on the 1st of June this year. Enrollment information could be extracted through the BIOS platform, and the weekly enrollment reports were sent to our partners to see the progress of the course delivery. As of December this day, 2020, the total course enrollments for every version, all 8 languages of the course, exceed 1,000 in particular. There are 1,084 enrollments, total enrollments, 338 active trainees, and already 98 certified trainees. Active trainees are considered the ones that have participated in at least one quiz, that have answered at least in one quiz. In a further analysis regarding the trainees of the English version, the participation per country is presented. Per country of the BIOS consortium is presented. In total, there are 103 active and 22 certified trainees. Viewing the participation of the active trainees per module, we can see the percentage of the trainees who participated in quizzes and final exams of each of the 4 modules. Further analyzing the data of enrolled trainees, there is information about the age range of enrolled of the participants, as well as their professional background. Indicatively, a large percentage of trainees are between 36 and 45 years old, while respectively 4 out of 10 trainees are medical doctors, as you can see in the graph. Monitoring one of the key performance indicators, the ratio between female and male trainees is approximately 1:1, and the percentage of certified trainees is close to 10%. Every successful trainee is eligible to receive a BioS certificate through the VLE, digitally signed on behalf of the BioS Consortium by Dr. Yannis Yalelis, who is the scientific coordinator of the University of Patras for the BioS project. This unique certificate is generated through the Progress tab in the BioS platform and can be downloaded in PDF format. Every trainee who participates in the course is asked to fill in a post-course survey through the BioS MOOC and evaluate the course. This questionnaire includes questions related to various aspects of the course, and the answers are studied and taken very seriously for further improvement and development by the BioS staff. The answers given by the trainees are collected and contribute to conclusions regarding the delivery of the course. This data is evaluated by the BioS staff, and where possible, the necessary adjustments are made in order to make it more effective. Considering all recorded comments, remarks, and requests of the trainees, through emails, forum topics, and questionnaires, improvements were made during the first round, but also in the view of the second round. All technical issues reported were fixed, and all proposals from BioS staff, trainees, and instructors were implemented by the technical team of Skybridge. Regarding the educational material, all possible interventions related to the notes of the trainees were implemented by BIP. If BioS trainees have any questions or face any issues while participating in the course, they can create a topic in the course forum and interact with BioS instructors or other learners. The instructors occasionally send bulk emails to inform the trainees about the progress of the course, to notify any updates, and to remind them that they are at their disposal in case they need any clarification. The online consultation was introduced in the second round of the course. These sessions were held live, and the trainees could ask questions and discuss with BioS instructors. All sessions were recorded and are uploaded to the BioS MOOC. The 3 online seminars were held, coincided with the Erasmus Days event from the 15th to the 17th of October this year. In these webinars, trainees had the opportunity to interact online with the hosts and answer online questions about the course content. This was a good chance for them to experience a more simplified and practical application of knowledge offered through the BioS course. The sessions were recorded and uploaded in the BioS MOOC. The first webinar was organized by INEOS, and 53 participants attended. 39, sorry. The second webinar was organized by BGU Murnau, themed computational statistics for clinical doctors, and 44 participants attended. The third webinar was organized by the GOC, and 32 participants attended. In total, in all 3 webinars, 22 of the participants were at that time certified BioS trainees. Detailed content regarding the WBL webinars will be presented to you in the workshop following this event. To conclude, I would like to point out that despite the extraordinary global situation, since the course is addressed to medical doctors and health professionals in general, the findings from the course delivery show that a constantly growing global community with great impact in the field of bioinformatics has been created. Thank you very much for attending. Laura.
Microphone.
Sorry. I had a full introduction already spoken. So thank you very much, Elias. We will now conclude the session on BioS project with an input from Professor Guglielmo Trovato, representing the European Medical Association, speaking about the BioS dissemination, our policy briefs and recommendations. Thank you very much, Professor Trovato, for being here with us today.
Thank you, everybody. My task is very easy because the speakers displayed very well the main reasons of learning and practicing bioinformatics and of teaching and learning bioinformatics by so an advanced course. Can I have my slide? Okay, very well. And yes, I am the speaker on behalf of the European Medical Association, which has among its commitment also increasing literacy and ethics in medicine and in science. Dissemination is a very relevant task in this case. Basic dissemination activities were for us newsletters sent to what we call stakeholders, which means in numbers 50,000 medical doctors, all European Parliament members, several stakeholders inside scientific societies, medical societies, medical student societies. There are 3 important medical student societies for a total of about 20,000 persons. And the other basic dissemination activities, because it's the main view of any project, is the BioS website, which is managed by Skybridge. We used social media channels. Everybody can understand why. This is a digital project, and with dedicated pages. I mean BioS pages, but also European Medical Association pages on LinkedIn, on Facebook, and the account of Twitter. The number of followers is written here, no problem, but is more important the number of members reached inside the scientific and professional groups. What I mean? I mean that inside LinkedIn, the European Medical Association and me personally are member of professional group in bioinformatics, in medicine, in e-medicine, in e-health, everything you can imagine inside the new and the innovative digital science and digital medicine of the future. Basically, we published 4 articles in peer-reviewed journals with impact factor, of course. We organized 4 international conferences and delivered 6 policy briefs and 1 policy recommendation. This is only the core of the publications and of the activities in this sense, because also the other partners did this kind of tasks, some other pathogens, not all, of course. Which is the meaning of this so naive drawing? The meaning is that we need to be clear. We need to be clear with people. I appreciate very much the scientific talks, but here we must display the reason of our need of disseminating literacy, attractiveness, and interest to bioinformatics and the course itself. I am receiving some suggestions from the coordinator, but I cannot see so easily going from one side to the other. Anyway, which is the rationale of the BioS project? Unmet needs analysis. We went back for increasing interest of audience, stressing on unmet needs, as pointed out, for instance, by the European institution, by the international scientific institution. This is a strategy important in this sense. We cannot only go forward by assertion. We must go forward discussing and putting evidence to our audience. Where is the place of bioinformatics? Is probably in the base of what we call healthcare, precision medicine, and is the base for several components of omics, diagnostics, therapies, and clinical risk analysis. Why this Greek temple? Because bioinformatics is not, and computational biology is not only a, how can I say, a tool, but is something in between theory, hypothesis, model, statistics, and the effects of all this. I understand that I am talking a very basic language, but this is my language. So, what is the strategy? This is a part of the policy briefs and policy recommendation we addressed. For involving persons in the interest toward bioinformatics and the course itself. This is a scheme, an infographic scheme. And also it should be clear to most of our, was a question of all the audience, who is a bioinformatician? What is going to do? It's very important to be clear in this sense, and which are the possibility, opportunities of study, of work, and so on. So, this is a scheme, the 10 challenges of a project like this, but very similar to other projects. Challenges before the intervention, during the intervention, after the intervention. What is the reason of this scheme? This scheme was drawn mainly for being clear with policymakers. We cannot make a lesson on bioinformatics or whatever we wish, even a sample, but we must say how was the reasoning for going forward. And we must also be clear what we would like to do after the project, how we can ensure the post-interventional impact. I have only 1 minute, I guess. Doesn't matter. And this is the infinity loop of any course, but also, and mainly when we perform education science project. This is the life cycle, a continuity of endless cycle adaptation. I would like to stress that all these points are part of previous publication on peer-reviewed journals from inside the group, not from outside. And last, link between bioinformatics and artificial intelligence. This is very important. And we put this topic in most of our dissemination posts in the social media. And this is a task very important in the view, the current view of the current Commission and the current European Parliament. Learning tools. What is a learning tool? Every learning tool is not a way of implanting something in the brain of somebody. This is a strategy, and the strategy must be clear. We tried to show inside the dissemination, and you saw which
Hi, Guillermo, I think we lost you. Okay, I can see here that he has trouble connecting. He seems to be back on. Guillermo, can you hear us? Okay, let us, this can happen. It's an online event. So I see he's back in the team.
okay. So this is the last slide, in which there is the commitment also of the European Medical Association to follow the task of disseminating also for literacy in bioinformatics, but in every field of science related to medicine, news and also directives from the European Commission. This is our commitment since 30 years. Thank you very much.
Thank you very much, Professor Trovato, for your speech. And now we will commence the BioS workshop, which will be conducted by our partner, Enius Application and the German Oncology Center. I'm happy to introduce to you Maria Nicolau, starting the workshop on genetic methods and application in patient treatment. Thank you very much, Maria.
Thank you, Laura. Firstly, I would like to say thank you to all the presenters for the very interesting talks. My name is Maria Nicolau, and I will assist you during the first part of the workshop. In our pre-recorded seminar we are introducing today, we will focus on the commercial personalized genomic services in patient care. The seminar will emphasize on next-generation sequencing and applied bioinformatics, and our collaborator, Dr. Alexia Riadis, will guide you through her presentation. At the end of the presentation, we will be using Mentimeter so you can interact with us. You will be asked to answer a few questions regarding the seminar. More information will be explained later. Now, let me give the lead to Dr. Alexia.
Hello everyone, my name is Alexia Liades. I'm a senior scientist at NIPD Genetics in Cyprus, and this is a company that specializes in research and development of genetic tests using next generation sequencing methodology for different fields in medical diagnostics such as prenatal diagnosis, reproductive health, and oncology. So the focus today will be the application of next generation sequencing in oncology diagnostics. So in the following slides, I will go through the basic principles of next generation sequencing, or NGS for short, and I will show how it can be applied in the clinic for assessment of the molecular profile of the disease that can help guide the doctors to the most appropriate treatment. Next, I'll describe the NIPD Genetics developed test for tumor molecular profiling, and I will focus on the clinical utility of such tests in the diagnosis and treatment of non-small cell lung cancer. Next, I spend a couple of minutes on the importance of genetic testing for the diagnosis of hereditary cancer, predisposing syndromes, and finally, I will talk about a non-invasive approach in oncology diagnostics, which is termed as liquid biopsy. So in this video, you can see the improvements in the rate of DNA sequencing over the past 30 years or so and into the future. From gel-based systems to capillary sequencing and second-generation sequencing technologies, there has been more than a million-fold improvement in the rate of sequence generation over this time scale. DNA sequencing as we know it originated in the late 1970s when Frederick Sanger at the MRC Center in Cambridge developed a gel-based method that combined a DNA polymerase with a mixture of standard and chain-terminating nucleotides. When visualized with a gel electrophoresis, one reaction per lane, the fragments are sorted by length, and this allows DNA sequence to be read off base by base. So this technique was revolutionary at its time. It enabled the sequencing of 500 to 1,000 base pair fragments. By the 1980s, Sanger's original method had been automated by scientists at the Caltech, and large slab gels were replaced with acrylic finer capillaries. This technology, which was continuously improved over the years, served as the bedrock for the Human Genome Project. Now we're in the era of massively parallel sequencing, or next generation sequencing as we know it. The NGS platforms are now the dominant type of sequencing technology used today. Their extreme capacity allows for sequencing at a very low cost with a very high sensitivity. Today, these high-throughput sequencing technologies have been applied in a variety of ways, such as whole genome sequencing, targeted sequencing, gene expression profiling, epigenetics, chromatin immunoprecipitation sequencing, and small RNA sequencing. And this really accelerated biological and biomedical research. In the context of this presentation, we will focus on targeted sequencing that allows deep sequencing of specific genomic areas of interest. In NIPD Genetics, we have leveraged the powerful technology we have developed for our prenatal diagnostic solutions, and we have tailored it to deliver superior performance, high accuracy, and reliability in the context of hereditary and somatic cancer testing. Briefly, the technology relies on a targeted design of probes called tags, and this is short for targeted capture sequences, which are coupled to magnetic beads. This in turn results in the activation of the captured constructs, which are then used to capture fragments of interest from the DNA library. This results in an enriched library of the targeted DNA fragments that are bound to the probes with high efficiency. The fragments are then eluted from the probes and subjected to NGS sequencing. Lastly, the sequencing data are then analyzed using bespoke bioinformatics pipelines. So what happens when the samples are loaded on the sequencer? So we are using a sequencing by synthesis NGS technology. And this technology uses the so-called bridge PCR for clonal amplification of individual DNA fragments. This PCR is performed on the flow cell, and this is a glass slide which is similar to a microscope slide, and on which the actual sequencing takes place. DNA fragments are linked via the adapters to the flow cell, and then bridge PCR is carried out. Oligos bound to the flow cell function as kinase, and each individual DNA fragment forms a separate cluster of identical DNA fragments. And sequencing by synthesis is based on the cyclic reversible termination, or CRT method. Each of the 4 nucleotides is linked with a different dye and modified by a terminator group. During a reaction cycle, all 4 nucleotides are offered simultaneously to the polymerase for strand synthesis. After incorporation of a complementary nucleotide strand, elongation is no longer possible due to the blocking effect of the terminator group, and the 4 dyes of each nucleotide can be detected using imaging. The dye and the terminator group are keyed, and the new synthesis cycle starts. The sequence of each cluster is thus simultaneously determined base by base. Using sophisticated bioinformatics, individual base sequences, reads, are aligned to and compared with a reference genome for mutation detection. Moving on now to the clinical utility of NGS in cancer diagnostics, we are now witnessing a fundamental change in cancer treatment in recent years. We're moving from a histopathologically defined tumor towards a genetically characterized disease, and this paves the way for targeted therapy. So there are now increasing requirements in molecular pathology for molecular testing, and it's now becoming a part of any patient with cancer. So now the challenge for clinical centers is to provide molecular testing so they can provide information for targeted therapy. And you can see in this graph the ever-increasing number of association of gene variants or gene mutations with drug associations. There are more than 700 variant gene-specific drug interactions with consensus or emerging therapeutic relevance. And as you can see here, lung adenocarcinoma is the cancer type with the highest number of gene variant drug associations. This need for advanced molecular tests in the ever-demanding field of tumor diagnostics is what we strive to fulfill. So we developed the Forsentia genetic test that aim in identifying and analyzing clinically actionable variants across the wide spectrum of solid tumors. So Forsentia builds upon our existing technology to offer testing that will improve molecular classification of the tumor in form of available targeted therapies and the possibility to enroll in clinical trials. And it aims in improving the diagnosis and overall empower the clinician to offer a better informed clinical management. Just to briefly touch on the Forsentia somatic cancer test panels, the Forsentia offers extensive analysis of clinically actionable mutations that are implicated in many cancer types. It offers molecular classification of the tumor, and it's based on the NIPT genetics precision technology, which offers high sensitivity and specificity and reliable diagnostics. So we aim in identifying clinically actionable alterations that have a prognostic value or can guide treatment decisions, which can elevate the chances for successful treatment through precision medicine and targeted therapies. And with Forsentia, we offer 2 categories of genetic tests. We have 6 comprehensive cancer-specific panels that aim in analyzing a specific set of genes that show high association with specific cancer, such as breast and ovarian, colorectal, prostate, glioma, melanoma, non-small cell cancer. We also offer a pan-cancer genetic test, which covers 76 genes with clinical actionability. And we also have a group of therapy-associated panels, which focus on a single or two gene testing, and these are genes that are directly associated with specific targeted therapies. So therapy selected panels are carefully designed for their clinical actionability and their association with targeted testing and the necessity for testing in order to receive a selected targeted drug. So these panels focus on the identification of single nucleotide variants or indels, small insertions and deletions in hotspot regions of the genes tested. And this is cost competitive with a short turnaround time, and they're routinely requested by oncologists. And there are several approved targeted therapies and ongoing clinical trials focusing on these genes. So for example, EGFR testing is required before the patient receives any of the EGFR targeted therapies. KRAS and RAS positive patients show resistance to selected drugs, and PI3K positive patients in metastatic breast cancer are eligible to receive PI3K inhibitor treatment called alpelisib in conjunction with fulvestrant. BRAF positive patients can receive BRAF inhibitors, and INDH1, INDH2 is an important biomarker classification of glioma. And several clinical trials are now testing INDH1, INDH2 inhibitors in the context of glioma treatment. All the technical advantages of the NIPD genetics technology enable our unparalleled accuracy for single nucleotide variant, indel detection, translocation, as well as copy number alteration detection, with very high sensitivity and specificity that allows the identification of clinically actionable somatic alterations at even low variant allele frequencies. And all these features maximize the diagnostic power of these tests. Forcentia has a very simple process. The only thing needed is a sample from the tumor biopsy that has already been performed and sent to the histopathology lab. So there's no need for the patient to have another procedure. After the sample is received in the NIPD genetic lab, the results are sent to the healthcare provider within 2 to 3 weeks. Moving on to the clinical case we're presenting today. Non-small cell lung cancer is the most common type of lung cancer, and it's a tumor with a broad spectrum of targeted therapies that are either already available and approved by drug authorities, or they are investigated in clinical trials. The molecular characterization of non-small cell lung cancer tumors using next-generation sequencing technology has really become a key tool for facilitating treatment decisions and the clinical management of patients with non-small cell lung cancer. As you can see in this graph, these are data retrieved from the catalog of somatic mutations in cancer from the Sanger Institute in the UK, and they show the molecular mutational spectrum of the tumors analyzed, with EGFR being the most frequently mutated gene in non-small cell lung cancer, followed by KRAS, TP53, as well as other genes with lower frequencies in non-small cell lung cancer. NIPD Genetics offers the Forcentia non-small cell lung cancer gene test that includes 35 genes covering single nucleotide variant, indel detection, copy number alteration, as well as translocation detection for the selected genes. Then genes are carefully selected based on their association with approved therapy or with emerging therapeutic relevance, or they offer prognostic information. As you can see, the genes highlighted in red are the genes that are included in professional guidelines such as the National Comprehensive Cancer Network. In the table shown here is a list of genes recommended for testing by the National Comprehensive Cancer Network, along with their significance, And in the last column, you see the list of percentage tests that cover that specific gene or variant. For example, EGFR deletions on exon 19 or the exon 20 L858R substitution show responsiveness to tyrosine kinase therapy, and EGFR testing is included either in the non-small cell lung cancer panel or as a single EGFR testing panel or as part of the comprehensive pan-cancer panel covering 76 genes in total. Another example is ALK rearrangement, which show responsiveness to ALK tyrosine kinase inhibitors, which show improved efficacy for alectinib over crizotinib, and they're included either in the pan-cancer panel or the non-small cell lung cancer panel. Here you can see a summary table of targeted therapy or immunotherapy for advanced or metastatic disease in non-small cell lung cancer that is used either as first-line therapy or subsequent therapy. So genetic testing for the indicated genes is required for the administration of the associated targeted therapy. Now to switch gears a bit, another important aspect of oncology diagnostics is genetic testing for hereditary cancer predisposing syndromes. Obviously, the foremost benefit for hereditary cancer testing is the identification of individuals that are carriers for pathogenic variants that are associated with cancer predisposing syndromes. And this information can enable clinical action to be taken in order to reduce the risk of recurrence in patients or the risk of primary cancer in family members. For carriers with high-risk mutations that are very likely to develop cancer, prophylactic surgery is often the most preferred option. Overall, there are a lot of data that show that genetic testing and prophylactic surgery that is taken upon diagnosis can actually reduce the risk of cancer by even 90 to 95%. There is also a therapy potential in identifying mutations that can improve chemopreventing therapy and introduce targeted therapy in patients that are identified with a pathogenic variant. An excellent example of such case is the patients with a diagnosis of breast cancer that can receive PARP inhibitor treatment if they are positive for BRCA1 or BRCA2 mutation. Now, who should have hereditary cancer testing? Well, there are a lot of professional recommendation guidelines that suggest testing when there is a suspicion of a hereditary cancer syndrome. And there are some clinical features that are suggestive of such a syndrome. For example, when a cancer is diagnosed at an unusually young age, or if a person is diagnosed with several different types of cancer, or multiple primary tumors, such as bilateral breast cancer, or even when there is a lot of blood relatives from the same side of the family that are diagnosed with the same cancer type, or if there is an unusual representation of a specific cancer type, for example, breast cancer in men, and the presence of certain phenotypic characteristics that are associated with certain syndromes. Ancestry is also important. As you know, Ashkenazi Jewish ancestry has a higher probability of harboring hereditary mutations. And lastly, the occurrence of some cancer types have higher probability of harboring pathogenic variants, such as triple-negative breast cancer or epithelial ovarian breast cancer, or colorectal cancer with mismatch repair deletions. There are certain clinical scenarios that multi-gene panel testing is recommended. For example, when the personal or family cancer history meets more than one hereditary cancer syndrome criteria, the doctor might choose to test more than one genes. In addition, when there's a personal history of multiple cancer diagnoses, it's usually hard to pinpoint a specific hereditary syndrome. So the doctor might choose to test for multiple genes in order to increase the probability of identifying a pathogenic variant. In addition, when a first-line testing is inconclusive, the doctor might choose to test for a higher number of genes. For example, when you have a breast cancer patient with a suspicion of a hereditary cancer syndrome, and that patient underwent a first-line testing for just BRCA1 and BRCA2 genes, if that testing was negative, then the doctor might choose to offer testing for a higher number of genes to increase the probability of identifying a pathogenic variant in genes that go beyond the BRCA1 and BRCA2. And lastly, when there's a truncated family history, either due to adoption or family members dying in a young age for reasons unrelated to cancer, or even when the pedigree is lacking representation of the opposite test, the doctor might offer multi-gene panel testing. The clinical utility of multi-gene panel testing is documented in multiple studies, as you can see here, that show a higher percentage of patients with pathogenic variants is identified when a large number of genes are tested, as compared to just a single or two-gene testing. So multi-gene testing in this setting is likely to alter the near-term cancer risk assessment and management recommendations for mutation-affected individuals across a broad spectrum of cancer predisposing genes. So the procedure for presenting hereditary cancer testing is very simple. We request a background swab to be sent to our laboratories, where the sample is processed and analyzed, and then a very comprehensive report is generated and then sent back to the clinician within 2 to 3 weeks. We have done an extensive review of the literature. We followed guidelines from several regulatory bodies, and we also consulted with oncologists and medical geneticists in order to develop genetic hereditary cancer panels with the maximum clinical utility. So you can see here the 19 gene panels for hereditary cancer testing. We covered a broad spectrum of cancer types, and we also include a pan-cancer gene panel covering 62 genes that are associated with cancer predisposing syndromes. And in all these panels, we can accurately detect different types of genetic alterations, including single nucleotide variants, small insertions and deletions, as well as copy number variations for all the genes included in these panels. In total, presented tests cover 24 hereditary cancer predisposing syndromes. And in this table, you can see all the syndromes covered in the different hereditary cancer panels. You can see here the unique Fram-Wenny syndrome with the TP53 gene, hereditary breast and ovarian cancer syndrome, testing for BRCA1 and BRCA2 gene, familial adenomatous polyposis covering the APC gene, and so on. So here you can see examples of the hereditary pathogenic mutations identified. Here is a single nucleotide variant identified in the BRCA1 gene. This is a T2G mutation that results in a cysteine to glycine substitution at position 61. And in this example, you can see the ability of our method and our bioinformatics algorithm that can reliably identify a deletion of 23 base pairs in the BRCA2 gene that results in an early termination of the protein sequence. Moving on to the patients that harbor small exonic deletions. These are patients that show deletions in the BRCA1 and MSH2 genes. The first is an example of a patient that we have identified a single exon deletion on BRCA1 gene, and this is exon 20 that was completely deleted. This is a second example of, again, a single exon deletion, this time on exon 23 of the BRCA1 gene. And the third one is a patient that had 7 exons deleted on the MSH2 gene. this is associated with the Lynch syndrome. To finalize, I hope I was able to convince you of the value of genetic testing in oncology. Here in NIPD genetics, we have a validated technology that covers multiple types of genomic alterations, and we provide quantitative and sensitive detection of variants with very high accuracy, sensitivity, and specificity. So the targeted NGS method that we use and the careful selection of the content of these genetic panels ensures a high clinical impact of these tests. For the Presentia hereditary cancer test, information from this gene testing can enable early diagnosis, inform the clinician to make the appropriate clinical management, prophylactic surgery, and reduce the risk of developing cancer. In the case of Presentia somatic cancer testing, we offer a deep investigation into the tumor and offer information that can guide clinical therapy and inform on relevant clinical trials and offer prognostic information and overall a better clinical management. And to finish up, the next frontier in oncology diagnostics that is increasingly gaining ground is liquid biopsy. This is a non-invasive approach to molecularly characterize the tumor by the analysis of cell-free tumor DNA that is shed from the tumor into the bloodstream. So at NIPD Genetics, we are now developing a liquid biopsy test that can identify tumor-related mutations in the patient's plasma. Liquid biopsy testing can be used for the diagnosis of cancer or in order to detect residual disease after surgery, to monitor response to therapy, as well as follow-up monitoring throughout treatment, and to detect genetic alterations that are associated with drug resistance. This application can actually have immense clinical utility in various solid tumor malignancies, including non-small cell lung cancer. For example, liquid biopsy can be used for monitoring response on tyrosine kinase therapy. If during tyrosine kinase treatment, a resistant EGFR T790M mutation is identified, then the doctor can decide to change the treatment and give the patient osimertinib, which is a third-generation tyrosine kinase inhibitor that is approved for patients with this type of genetic mutation.
Thank you very much. I would like to thank Dr. Alexia for her very interesting talk. Now it's time for some questions. I would like to ask you to open a new tab in your web browser and enter this specific address here, which is www.menti.com, and insert this code here. I'm also gonna share my screen so I can show you a demonstration of how it's done. So if you please follow the web address, which is www.menti.com, and the code is 7804750. So I prepared some questions, and you have the opportunity to answer the questions and choose the answer that you think that is correct. I'll give you a minute to prepare the tab. So I'm repeating, the code to connect is 7804750. Okay, let's try to go to the first question. So, first question. Targeted next generation sequencing refers to A. Sequencing of selected genomic loci of interest. B. Sequencing of all the exons in the genome. C. Sequencing of the non-coding regions of the genome. Please vote for your answer. Okay, let's see what's the correct answer. So, as most of you voted, the correct answer is A, sequencing of selected genomic loci of interest. As you probably understand, the term targeted indicates sequencing of specific gene regions of specific interest. Exons and non-coding regions refer to sequencing of a much wider part of the genome. Let's move on to the next question. Deletions in exon 19 of the EGFR gene are of clinical importance because they result in a loss of function for the gene. B, they show sensitivity to osimertinib. C, they show responsiveness to trastuzumab treatment. Please vote for your answer. Okay. The correct answer is B. They show sensitivity to osimertinib. The identification of a deletion mutation at the specific gene has been linked to the specific drug according to scientific research, and it is further used nowadays for clinical application. Next question. Hybridization capture targeted next-generation sequencing refers to A. The use of PCR amplicons at targeted genomic loci. B. The use of biotinylated probes designed to capture regions of interest. C. Sequencing the complete DNA sequence. And D. Chip sequencing to analyze protein-DNA interactions. Please vote for your correct answer. Okay, most of you are correct. The correct answer is B, the use of biotinylated probes designed to capture regions of interest. The technique for the specific sequencing is based on biotinylated probes. And last question. Next generation sequencing testing in hereditary cancer refers to A, the identification of somatic mutations in the patient's tumor. B, gene expression profiling in selected cancer susceptibility genes. C, the use of identification of benign single nucleotide polymorphisms in the general population. And D, the identification of germline mutation associated with increased cancer risk. Please vote for your answer. Okay. The correct answer is D, the identification of germline mutations associated with increased cancer risk. Since we talk about hereditary cancer, we refer to germline mutations that are detectable within germ cells and are the only mutations that can be passed on to offspring. On the other hand, somatic mutations can occur in any of the cells of the body except the germ cells, and therefore are not passed on to children. We have reached the end of the presentation and the voting. So I think we can now have 1 or 2 minutes for break, and then my colleague from Ineos company, Marianne Logovetti, will take the stage. Thank you so much for your participation.
So, hello to everyone, and welcome to the second part of the workshop organized by Ineos. My name is Marianne Logovetti. I'm a postdoctoral researcher at National Technical University of Athens in biotechnology laboratory, and I'm also a member of Ineos Bioinformatics company. Through the current workshop, we will try to introduce you in the concepts of precision medicine and personalized therapy, how different therapy is applied based on the genetic background of each person, as well as to the meaning of the biological interpretation and how a bioinformatics company like Ineos can contribute in precision medicine and the extraction of biomarkers exploited as drug targets. Okay. From now on, you will watch a workshop focusing on the biological network-driven interpretation, signature extraction, and variant prioritization from whole exome sequencing data through the Bioinformatics platform that Ineos has developed. And then a small session including questions that you can answer through Mentimeter, like Maria showed you before, will follow. And finally, I will try to answer questions that may arise from the whole workshop. First of all, let me introduce you once more to precision medicine, which is an emerging approach for disease treatment and prevention that takes into account individual variability in genes, environments, and lifestyle for each person. With the rapid advancement of the technologies studying the genome, it is now known that the genetic background of each individual dictates the use of a different drug for the same disease, according to the particular genetic background of each human being. The most important steps in precision medicine are the sampling of genetic material, DNA or RNA, the digitization of the genetic code, and the analysis of data and biological interpretation. Biological interpretation includes the understanding of the particular genetic background and the identification of the specific drug that should be administered according to each person's profile. In the analysis of the data and in biological interpretation, the science of bioinformatics, as mentioned all this time, plays a very important role, including the application of mathematical algorithms for the analysis of biological information transferred through the genetic code. However, it has been shown that this final stage of biological interpretation significantly limits the precision medicine, as today a huge production of digital genetic data is performed, but all this amount cannot be easily analyzed. As briefly mentioned in the previous slide, the main goals of biological interpretation that follows the pre-processing analysis of the genetic data include gaining biological insight of the analyzed data, such as pathways or networks, and the derivation of biomarker sets that may serve as drug targets or may help in cohort specification of the patients that may further have predictive capacity. The difficulty in the biological interpretation that I mentioned lies beside the huge amount of data in the enormous complexity that the biological systems have. Biological information is expressed in the form of biological networks with very large dimensionality. And networks are made up of a large number of biomolecules which interact with each other in a very complex way. For example, Enios company develops technology for the rational analysis of the biological information. So the complex genetic data is analyzed through computational algorithms that extract useful information through biological networks. Enios has developed, for example, a computational platform that streamlines the data-driven derivation of personalized biomarker signatures, assisting the medical decision. So the end result is small signatures that contain only the useful information in a form of genes that can be drug targets. This identifies the appropriate drug that targets a specific biological mechanism and may have an increased effect of an individual or groups of individuals that share a common genetic background. In the case of precision medicine in cancer, we speak about precision oncology. In this case, for example, from patient clinical omic data obtained from state-of-the-art technologies such as whole exome data sequencing, RNA sequencing, and macroarrays, we go to personalized gene signatures that can be extracted and further exploited for pharmacogenomic profiling of tumors and finally to genomic-assisted therapeutic strategies. This whole approach has a starting point, the Human Genome Project, that focused on sequencing of the whole human genome, which may be now something very simple, as mentioned in previous sessions. The Human Genome Project costed almost $1 billion and was completed in April of 2003. It also set the stage for the evolution of genomic medicine the last 20 years. The human genome sequencing was the information bottleneck for exploiting genomic data in healthcare. More specifically, National Human Genome Research Institute defines genomic medicine as an emerging medical discipline that involves using genomic information about an individual as part of their clinical care and the health outcomes and policy implications of that clinical use. But despite the fact that we are aware of the human genome sequence, does not mean that we are aware of the way that it affects the human phenotypes and, most importantly, the diseases. The physicians have still a very long way until it is indeed utilized in medical practice, since the genome sequence data are very difficult to interpret. The first stage in the genomic research was to understand the structure of the genome through the sequencing of the whole human genome. The next stage is still focusing on understanding the biology behind these genomes, then to elucidate through this information the genomic component and biology of the diseases. So this knowledge will be further applied in the advancement of the science of medicine. And finally, the ultimate goal is to exploit the advancement in genomic research for improving the effectiveness of the healthcare. So the current state of the art, the technology based on which we determine the order of DNA building blocks in an individual genetic code, is next generation sequencing, or as we'll abbreviate it from now on, NGS. NGS technologies allow the massive parallel sequencing of the DNA. The sequencing is performed on fragments of DNA of the studied samples, and then these fragments are amplified on many clonal DNA molecules, and then massively and parallel sequenced. Here, I would just like to mention that the pieces of DNA that are sequenced by the sequencers are termed as reads. Two of the most widely applied NGS methods, whole exome sequencing and whole genome sequencing, are increasingly used in healthcare and research to identify the genetic variations. Both methods rely on NGS sequencing technologies mentioned. Whole genome sequencing determines the order of all the nucleotides in an individual's DNA and can determine variations in any part of the genome, whereas exons are thought to make up 1% of a person's genome, and the sequencing encompassing all exons of protein-coding genes in the genome. Together, all the exons in the genome are known as the exome, and the method of sequencing them is known as whole exome sequencing. Many genetic changes can be identified with whole exome and whole genome sequencing. Much of this information, though, has unknown significance, since not all genetic changes affect health, and it is difficult to distinguish, to know whether the identified variants are involved in the condition of interest, such as a disease. Continued study of exome and genome sequences can help determine whether new genetic variations are associated with health conditions, aiding disease diagnosis. Whole exome sequencing is thought to be an efficient method to identify possible disease-causing mutations. Many known mutations so far that cause diseases indeed occur in exons. For a typical individual, 60 million base pairs are sequenced, including 80,000 variants and 20,000 genes. Before I begin presenting you a specific part of analyzing whole exome data, I will try just to remind you a little bit some important definitions in this field of research. Mutations, for example, refer to modifications in any genetic sequence, and mutations may refer to small changes such as substitution of single DNA building blocks or larger mutations affecting many genes on a chromosome. SNPs, or single nucleotide polymorphisms, result from a substitution of a single base pair, such as here transversion event is happening, substituting a thymine nucleic acid in place of a guanine. Insertions and deletions, or indels, affect a strings of base pairs. For example, here you see an insertion string where a guanine, a thymine, and an adenine has been inserted, whereas in the second example, you can see a deletion event showing a deletion of ketosine and an adenine. Now, here you can see a very brief overview, a summarized overview of the analysis of a typical NGS experiment. So I will mention a summary of the first steps of the analysis, and then I will present to you, based on the web-based bioinformatics platform of ENIOS VCF Analyzer, a cloud-based workflow developed by ENIOS, the last step of annotating and filtering variants from whole exome sequencing experiments. So the first step includes the creation of raw digitized data from the sequencer, and that are provided in the form of FASTQ files. The FASTQ files include raw unaligned reads from the sequencing experiment, including some of the following records, such as the sequence identifier, the sequence, and some quality scores. The short reads that are generated by the NGS instruments in the form of FASTQ files are then mapped to the reference genome through the step of alignment. The reference genome is actually a nucleic acid sequence database used as a representative example of a species genome. Reference genomes are actually strings of adenine cytosine and guanine nucleotides that represent a complete set of genes from an organism. These genomes are stored in a database. So a reference genome is representative of a sequence of an organism's genome. So from a FASTQ file containing only DNA sequence, after the process which is called alignment, we move to BAM or SAM file formats. The next step includes the variant calling. Variant calling is a step of the analysis for the identification of differences between the sequence trees and the reference genome. This information is recorded in a file named as variant calling format file, or else its abbreviation VCF file. Differences in the reads compared to the reference genome are highlighted with blue color and are called variants. So variants can be defined as a specific region of the genome, which differs between sequence genomes and the reference genome. The following step is the variant annotation, the VCS foundation, on which we will focus on the specific webinar. Variant annotation actually has to do with gathering information about the biological effects of the variants. For example, through variant annotation, one can find out what gene does a variant affect, or if the variant affects a coding or a non-coding region, or even if it is a synonymous or a non-synonymous mutation. VCF text file format contains information about the identified variants, such as meta-information lines, header lines, and data lines, each containing information about the position in the genome. VCF files can also contain genotype information on samples for each position. More specifically, the VCF files include information about the headers, how the VCF file was created, and about variant records. If you look in more detail, the VCF data lines include information about the chromosome, which refers to the chromosome on which the variant is located. ID concerns the variant position on the chrome start coordinate of the variant. ID concerns a string identifier such as the BSMP ID. Ref is the reference allele that is found in the reference genome, whereas alt is the alternate allele found in the studied sample, referring to any base other than the reference genome. Qual is a quality score, and then filter includes a list of filters that the variant failed to pass, or the information that it passed the quality filters, flagged like pass. And these are the most important fields in this specific file. Here you can see an example of a VCF file including 3 recorded variants. The first variant describes a simple SNP in chromosome 20 at this specific position, where a guanine has been replaced by an adenine. As we can see, the specific variant has passed the quality control. The next, second variant is another single nucleotide polymorphism that has failed to pass the quality control. And the third one is another variant on chromosome 20 that has 2 alternative alleles, one in thymine in place of an adenine. So I have bombed you with all this information concerning the VCF files, included information, so that you can better understand how annotating and filtering variants in a VCF file from whole exome sequencing experiment can be exploited to extract specific SNPs, indels, and their corresponding affected genes in order to finally suggest possible drug targets. The analysis of the case study will be performed now through VCF Analyzer, which is a web-based bioinformatics platform developed by ENIOS. And the case study that we will present to you includes whole exome sequencing data from patients suffering from melanoma. In the specific study, I will present to you the diagnostic process, the workflow for the analysis of 2 patients with melanoma. In one studied cohort we have, the first one with the code T2D, and the second one T10D. So the 2 patients, after being diagnosed with melanoma, their medical history was recorded. Then a skin biopsy was obtained, histology followed, and then whole exome sequencing was performed. I will present to you how the VCF files occurring from the whole exome sequencing experiment of this specific patient was exploited for performing the bioinformatic analysis through ENIOS bioinformatic platform, and finally suggest a therapeutic intervention. The analysis of the genomic data from the whole exome sequencing experiment that will be performed through ENIOS platform VCF analyzer in less than 20 minutes extracts important information such as pathogenic gene variants related to a specific cancer for each of the examined patients, the chromosome and the position on which the pathogenic variant is identified, or the effect and the impact the variant has on the corresponding genes, and most importantly, the clinical significance of the identified variants. Generally, there are two main cases in melanoma concerning also the two patients we will show you with melanoma in our study. The first one concerns people that demonstrate BRAF mutation. Dimitrios has also briefly described that. I will say that again. So the first one concerns people that demonstrate BRAF mutation. In this case, the suggested therapeutic intervention includes BRAF inhibitors in conjunction with MEK inhibitors. And the other case concerns patients with NRAS mutations. This type of melanoma has still no targeted therapy, but still MEK inhibitors are either wise administered in combination with second-line chemotherapy or immune checkpoint. So, through the analysis of the exome data from this patient, the specific gene variants I mentioned you concerning these two cases can be identified and exploited, combining the genetic predisposition of these patients with their medical history, and finally, help to perform the genetic counseling concerning the final therapeutic intervention. So the gene panel that I will show you that will be derived by Infominer provides also other suggested therapeutic alternatives. So in this case, we have the VCF files from the two melanoma cases of the two patients, which through our analysis have the specific mutations I mentioned you. And overall, we will first perform the annotation and filtering of the variants with the VCF analyzer, and then through Bioinformatics, we will perform a blind or supervised analysis to assist the frontline clinical decision. So for each VCF file, one for each patient suffering from melanoma, we perform the following analysis. So now we'll go to bioinformatics.com. Just please give me a second. So then you go to bioinformatics.com, then you either make a new account. Obviously, I already have one. So I type my username and my password. I sign in, and then I create a new project. The title is mandatory. The description is optional. You can also invite other people in this specific project to edit or perform analysis. Then you can upload the files, the VCF files you want to analyze. For example, this is the VCF file for the patient T2D, which I have already uploaded. And then we go back to my project and we create a new experiment. Here, the platform provides you with three options. The first option is running by Infominer immediately, where the input is a gene list for biological interpretation for an enrichment analysis. And the other two options provide the option to perform the steps of variant annotation through the user-friendly tool VCF Analyzer, skipping all the laborious steps that require programming skills. In this specific case study, we will use VCF Analyzer Cancer. Since VCF Analyzer is adjusted to handle cancer exome sequencing data after having also incorporated databases for cancer data, such as Cosmic, which is a global resource for knowledge based on the world literature about somatic mutations in human cancer. You can also read the description for further information about the databases that are incorporated in a specific tool. Then experiment title is required. First, we can the example can be for the patient T2D. You can also you can also add the description, which is optional. Then you select the VCA file among the ones you have already uploaded. I select for the patient T2D. Then you can select among the reference genomes that are available. For example, if you go back to the file preview, you will see that for the specific patient, the reference genome that has been mapped to is 8G19. The specific file is single sample. It has only information about the variants on this single sample. Then the next step includes the pre-filtering of the variants. Minimum and maximum alleles is a field that allows you to filter data with as many alternative alleles as you choose. So here we select 2. The next step allows the user to keep all the info values from the original file. Additionally, it allows you, the user, to remove all sites that did not pass quality control from previous stages. And the next step includes genomic annotation as well as filtering of genetic variants based on the effect prediction according to sequence ontology, a database with standardized terminology for a uniform description of the impact of sequence changes. The user can select among effects of single nucleotide polymorphisms and short insertions and deletions, such as missense variants, nonsense variants, or stop-loss variants, etc., as well as in spliced site regions, such as spliced region variant, etc. For example, I just want to remind you, frame-shift mutations according to sequence ontology refers to an attribute describing a sequence that contains a mutation involving the deletion or insertion of one or more bases where this number is not divisible by 3. Nonsense mutations, for example, refer to a sequence variant whereby at least one base of a codon is changed, resulting in a premature stop codon, so leading to a shortened polypeptide. Or, for example, missense variants, according to sequence ontology, are sequence variants that change one or more bases, resulting in a different amino acid sequence, but where the length is preserved. The last available custom filter options of the workflow include functional and frequency filtering. So the frequency filtering can be exploited by the user in order to assess the frequency of both SNPs and indels in widely used databases, such as Exome Aggregation Consortium or Exome Sequencing Project, etc., and allows to the user to keep the variants based on their respective minor allele frequency thresholds. So it allows the user to keep whether he wants rare variants, etc. It is very important to say here that it's important to be aware of the fact that for each step of the analysis that I presented you, usually someone will probably have to run a different bioinformatic tool designed for each step of the analysis and track a specific command, having to choose among a number of possible parameters. So bioinformatic tools like VCF Analyzer aids the analysis of whole exome sequencing data, providing useful information and most importantly, eliminating the need for advanced bioinformatic skills on behalf of the doctors, for example, that would like to analyze such data. So after running the specific experiment for each of the 2 patients, which I will not do now because it lasts about 20 minutes, its analysis, the running of its analysis. So we have already performed this analysis, and we will go to the results. So let's go to the results for patient T2D. We can see if the results, we go to results section. Here you can see the results of the identified variants, as well as the corresponding annotated genes. Here you can see that you can also see the chromosome on which the variant are identified, the position, the reference and the alternate alleles, etc. You can see also the list for the SNPs and you can go back and forth to see all the chromosomes. And also you can see the resulted list for the indels variant. You can also, their platform also gives you the opportunity to filter the variants according to your needs. For example, if you want only pathogenic variants, you can select pathogenic. Or if you want variants with high effect. And so if we search in the gene list here, if we search in the gene list, in the indels, we can identify the gene BRAF. So here you can see that the specific patient has a frame-shift mutation in the gene BRAF, which means that it belongs to the first case of melanoma patients I mentioned you before with BRAF. So after the variant annotation step I showed you, you can also perform the variant annotation step show you the results, which can also be shown in the form of graphs for its, for example, for the effects, the indels in form of percentages, and it also gives you the report where you can see a summary of the parameters you have chosen, as well as all the results summarized in one file that is downloadable. So after the variant annotation, you can also perform, you can also run Bioinformatics either through copying the list in the tool I showed you before, or through VCF Analyzer, and perform the biological interpretation and connecting the resulted genes with the enriched biological terms. So let's go to this result for the patient T2D. So here you can see the results. Here you can see the enriched ontological terms related to the variants you have chosen. And even more importantly, Bioinformatics gives you a gene signature, a compact gene signature related to the specific disease. And also, you can identify the variants related to each of these genes. So you can extract a gene signature related to the specific disease at the variant level. So truly exploiting the results from a whole exome sequencing experiment. So this time you perform systemic interpretation based on the variants. So as we mentioned before, due to the fact that the variant is identified in the BRAF gene, the specific patient will be suggested to receive BRAF inhibitors in conjunction with MEK inhibitors, such as vemurafenib, and also with the specific patient will be treated with MEK inhibitors, such as cobimetinib. But additionally, based on this gene signature, some alternative drugs are suggested. For example, for the patient T2D, based on the prioritized gene TP53, this DS cell adhesion molecule, which are involved in the systemic process of lipid transport and cell adhesion, the following related drugs are suggested: paclitaxel, which is a chemotherapeutic agent marketed under the brand name Taxol, among others, and carboplatin, which is suggested as an organoplatinum compound that possesses antineoplastic activity. So if we go to the respective analysis for the patient T10D, we can see that we can see in the results that NRAS missense mutation is identified. So he belongs to the second category of melanoma patients. If we also go to this patient's gene signature, extracted gene signature, First of all, the fact that he has this specific mutation means that he should be treated otherwise with MEK inhibitors, such as cobimetinib, and additionally, that he should receive second-line chemotherapy, such as paclitaxel and others. But also, some other alternative therapies are suggested based on this derived signature. For example, you can see NOTCH1 gene among the prioritized genes. It is a fact that NOTCH pathway plays an important role in the development of melanoblast, as well as the progression of melanoma, and NOTCH1 is considered a primary tumorigenic factor in melanoma. Now, two major classes of NOTCH inhibitors are currently in clinical development against NOTCH receptors or their ligands, showing encouraging evidence regarding decreased melanoma growth with antitumor activity. Also, according to the prioritized genes, you can also identify neurolegin-1, GRIT2, as well as complement protein 5, which are all involved in the systemic process of cell morphogenesis. And these are, so according to these specific genes, the following agents are suggested: fluorouracil, which is a pyrimidine analog of the xantinoplastic metabolite, L-glutamic acid, which is a homopolymer of glutamic acid, and eculizumab, which is a monoclonal antibody that targets complement protein C5. So let's go back to the presentation, which so I can say it now. So through this workshop, we tried somehow to introduce you to the secrets of multi-omic analysis with and the systemic interpretation, and how this whole process manages to reveal the active functional molecular modules, providing consistent mechanistic understanding of a myriad of interaction occurring, and enables in silico extraction of signature of molecular biomarkers for a more accurate and robust clinical diagnosis prognosis. We also showed you how the interpretation of the various types of mutational data was performed through the web platform Bioinformatics of ENIOS, integrating the results of diverse analytical workflows, and showcasing how to extract predictive signatures for several diseases without requiring advanced programming skills. So you had the chance to see an example of a data-driven interpretation and extraction of diagnostic signatures at the variant level, performed on a case study with patients suffering from melanoma cancer. At this point, I would like to thank all the ENIOS members participating in BioS course, as well as Georgia Kontogianni and Dimitrios Dulcinos, and finally, of course, all of you for your attention. So now, some questions will follow through Mentimeter, just like Maria has shown you. So first, you go to menti.com, just like before. Please open a new tab and press the code in the appropriate field, 8305363. And if you want to see the answers, you will go to Blackboard. And if you want to answer them, you will go to menti.com. I'll give you a minute to visit the slides, and you can directly answer the multiple choice questions that are presented, just like before with Maria's question. So, hopefully, most of you have entered the code 8305363. And let's go to the first question. The step of biological interpretation A involves the pre-processing steps of quality control, trimming, assembly, outer detection, and normalization. B involves the signal estimation step, e.g. variant calling. C involves the generation of target lists, such as lists with differentially expressed genes. And D follows the pre-processing analysis of the genetic data, providing biological insights of the analyzed data. Please select the correct answer. Now we'll show you the, okay. So the correct answer is the one that most of you have selected. Indeed, the biological interpretation is the step after the analysis, the pre-processing analysis, where you give biological insights of the data that have been already analyzed with all these bioinformatic tools and all this analysis. So let's go to the second step, to the second question. Order the following steps to deliver a computationally correct workflow from whole exome sequencing data, for the analysis of whole exome sequencing data. Number 1, alignment. 2, variant calling. 3, variant annotation. And 4, base calling. So again, most of you answered correct. It's first, it's base calling, then it's alignment, then it's variant calling, and this last step is variant annotation. Well done. What is the resulting file after completion of a typical bioinformatic analysis workflow for whole exome sequencing data and after the interpretation with Bioinforminer? The first A, FASTQ files including raw analyte reads from the sequencing experiment. B, some files containing sequence alignment data. C, VCA files containing information about identified variants after the variant calling step. And including a compact signature consisting of systemic processes and their driver genes, as well as their corresponding variants. Even if it's not clear for you concerning the file, for example, just remember that biological interpretation refers to the steps after the pre-processing analysis, where we try to gain the biological insight of everything we do through the bioinformatic analysis. So the correct answer is D. It's a PDF, a report showing a compact signature of biomarkers consisting of systemic processes and their driver genes, as well as their corresponding variants. Here you can see a screenshot from the results of VCF Analyzer after performing variant annotation that follows. How would you explain the fact that the number of the resulted variants and the number of the resulted genes is different? For example, how do you explain the fact that the gene BRINP2 is recorded 3 times? A, there is a mistake in variant calling. B, a variant may have a different effect. And C, a gene may have a variant in different sites. So there are 3 different variants in 3 different positions in chromosome 1 in the specific gene. So the correct answer is C. Indeed, a gene may have a variant in different sites. The variants can be through different positions in the genome. A frameshift mutation is a type of mutation involving the insertion deletion of a nucleotide in which the number of deleted base pairs is not divisible by 3, the insertion or deletion of a nucleotide in which the number of deleted base pairs is not divisible by 2, C, the copy or deletion of a nucleotide in which the number of deleted base pairs is not divisible by 3, and the copy or deletion of nucleotide in which the number of deleted base pairs is not divisible by 2. So the correct answer is A. And it is by definition, that is by definition a frameshift mutation. So we have ended this presentation. Thank you very much for attending and staying until now here with us. And Laura, I go back to you.
Thank you very much, both of you, for having conducted this valuable workshop. And with this, we now come to the end of the BioS event. I think once again, all the speakers present today and all consortium members having worked in the background to make this event happen, as well as the BioS project in general. The audience will receive a short questionnaire by email where we ask you to give us your feedback on our event. Thank you so much for your contribution. If you have more questions on the BioS project or the BioS course, please feel free to contact me. And with this, I wish you all the best and most importantly, stay healthy. Thank you very much.